bridge, the construction challenges and the design challenges, that sort of thing, in very brief. In the session 3, we discuss about the principles involved in bridge designs, how we're going to identify limit states, and in addition to that, when we were designing a bridge, the other aspects of the design we should know about, especially the fatigue design. And then we discuss about the some example about sign structures, and then I gave you different the design models we use when we were touch base with the material, common bridge design material, and then I show you like a different design code, for example, Australian standard and the American standards. The design approach against the Euro code or British standard, there's a bit difference, but more or less when you get the final outcome in the design, it's not exact, but quite close. So we are engineers. We don't go to closed form solution. We work with risk, and we make our own engineering judgment to solve the problem. So that's what we discuss in first 3 sessions. I would like to summarize the first 3 sessions as the part 1 and the foundation for you to understand about the bridge engineering. To be honest, when I'm in my career, I just build up through this. I never had this opportunity to learn bridge engineering like this. I had an opportunity to work with very experienced, very talented engineers, but and then while I'm working through the industry, I gain this knowledge. So I just explain you in the first 3 sessions, almost about 9 hours. If you want to be a bridge engineer, what sort of background you need to have. And I want to apologize that I think I didn't. I promise you I'm going to give you an assignment about some of the bridge engineering application to understand. For example, I want all of you to just to what you learned in the university about influence line diagrams, how you're going to apply. The reason I want for you to do that exercise, for you to get understanding when you are designing a bridge, is quite different to the other structures you design. For you to understand that, I just want you to do that exercise. But most likely, I think I will give this one this weekend, so you got a time to solve this one. So then we'll start the today's session number 4. And I think this slide you saw last 2 weeks ago as well, the bridge loads. We are designing a bridge for so many different loads. Those load include the weight of the structure. We categorize them as a dead load and the superimposed dead load. Bridges we primarily design for traffic load. You could see from these pictures these traffic loads. In addition to this, bridges are building in many different places, sometimes middle of the sea, sometimes in a valley, sometimes middle of the city. You can't name it, the place where you're going to build bridges. So therefore, it's going to subject it to significant environmental load, what we call wind load, flood load, and earthquake load. So when you are a bridge engineer, you need to have a really good understanding about each and every one of these load. For example, the environmental related load, earthquake, flood, and the wind, you can't see that one. You have to estimate this thing, and how you're going to apply them, and how you're going to make sure that what you are building is going to perform at least 100 years design life. When I went through the British standard and the Euro code, the expected design life of the bridge for these standards is 120 years. I think this is 120 years is the further stretched another 20 years. You need to have a significant QA, QC process to achieve that one with my experience, especially in the Australia last 14 years. To achieve 100 years also is really it's a massive challenge, but if you extend to 120 years, it's a lot. Then this slide I explained on the last session as well. I rushed through because it's a really long presentation the last time as well. The bridge load effects. I think when we were designing a bridge, for you to understand what we're going to, we categorize the bridge loads onto into three categories. The first one is permanent. It's never going to change. I mean, change in the sense the permanently inherent within the structure itself. The other one is transient effect, they come and go. And the other one is the thermal effect, of course, everybody knows about it. And the other one is the construction. That is the one of the specialized area, but as a bridge engineer, you need to have a better understanding what you are designing, how are they going to build that construction methodology, how is going to affect my bridge. So that is, at least you need to have some sort of background. So like if you are quite a young engineer, the construction loading sometimes is quite new to you, but if you are an engineer with some experience, you know exactly the construction, how it's going to affect the design. So when we talk about the permanent load, it's a dead load. Yeah, of course, the self-weight of the structure. Superimposed dead load is the form of dead load, but we use the superimposed dead load. You will see in the next slide. The earth pressure inherently we have it because we saw during the bridge element, behind the bridge abutment, we got a backfill. So we got throughout the design life, you got earth pressure. The creep and shrinkage, this is the time dependent creep, shrinkage, and the pre-stress, because most of the bridges, we use the post-tension and pre-stress segments. So the creep and shrinkage is a time dependent thing. Yeah, because it's going to affect your structure throughout the design life. The reason why creep and shrinkage is so effective in the bridges, because the bridges we use really long members, like you can say 10 meter to sometimes 200, 300 meters in length. And the pre-stress also is related with the creep and shrinkage. In addition to that one, I'm going to give you some hand. I will work out in the examples by hand, and I will put it in the resource folder. Like if you design in the pre-stress continuous span bridge, this pre-stress will produce what we call equivalent load. For example, if you profile in the continuous span bridge, your pre-stress or post-tension, the profile is parabolic. When you put that one in the parabolic shape through the along the bridge girder, that will produce what we call the equivalent load. So sometimes if you use the modern software, that will take into account, but if you just want to do a bit of a hand calculation to get your self-satisfaction, so it's better to understand that one. Another thing, as I mentioned before, the bridges are building on a very different ground condition. It could be rock, it could be like a sand and soil. Like for example, my experience in Bangkok, you can't find rock there. And then even within the Australia, different part of the country, we have a very as a continent I'm talking about, we have a very different kind of a geology. So I have experienced very a different kind of ground conditions because of that differential movement, because the bridges are long and quite high structures. The differential settlement in the structure will affect significantly. You can see in my background that bridge, about total height from the pile toe to the top is 120 meters. The length is 66 meters in the average span. If you go to the reverse span, it's close to 300 plus meters. Those will have a significant effect. And the forces from the bearing, because the bridges always support on the bearing. We mentioned that one. The bridge superstructure and substructure will be linked by a small element, that what we call the bearing. I just want to mention to you this one. This is I thought when I was preparing about bearing, first time in my life, I went to Polonnaruwa only one time and Anuradhapura only one time. And I remember I went to, when I was working in Bangkok, uh, uh, I got quite a number of years of experience in engineering, structural engineering. I got I can see things, I can understand a lot of things. I remember that I went to the place called Kuttampokuna in I think it's close to Mihintale, I believe. And that place, when I went, I saw all these remnants, and there, when I went to one place, I saw they built the old structure with the a piece of rock. It's like a slabs they create, and they got a drape ended at the end, and those end, when I closely looked at that one, they used the putty kind of a thing to make it as a bearing. So what I'm talking about, the sense of engineering, the people, when they build those things thousands of years ago, they had understanding about the behavior of the structures. So remember that I think especially you're in Sri Lanka, so most of you got those genes actually. So all the structures we build in our ancient structures, they have the kind of a significant understanding about engineering, the way they build. The good thing I think when I was that age, with that experience about structural engineering, when I went there, when I see this thing, I was able to understand. Like if I went there like a kid, or like when I was in the uni, maybe it's not the same story. Yeah. And then the water and buoyancy. Yeah, you saw many pictures. I saw you I think there were discussions in here as well. Some of the bridges went underwater. So this is the quite common thing. And then we put them as in the permanent category, but actually the water and buoyancy load, you can put them as in the transient category as well. And then this transient load, of course, the traffic load. And we understood traffic related another incident, collisions and impact. And when the traffic goes in and out from a bridge, it has to pass through the bridge abutment and to the embankment or approaches either side, that creates traffic surcharge. Of course, the earthquake is come and go. We don't know when, what is the magnitude, but we just estimate. And then the earthquake load, similar to the water flow, because if there's a flood, so it's not, we don't have it flood every day, but we get in the flood, we understood how we're going to categorize the flood, like the serviceability limit state flood is a 1 in 100 year recurrence interval, or in the ULS, so ultimate limit state, we consider 1 in 2000 year. And the pedestrian cycle and maintenance traffic, all those things is on the bridge, but it's not permanent, it's time dependent. And the fire loading also, the certain bridges, we just need to look at the fire design as well. For example, you can have a bridge is quite long, and the underneath you let the traffic to go, but if there is a tank or something blew up underneath that one, if that bridge is quite long, let's say the 300-400 meter, there's a tank blew up underneath, that heat might impact your bridge. So you need to look at the fire design, especially if you are designing a steel bridge, is very, very critical. So I'm going to discuss about fire design. I'm going to share with my experience in the North Connects Tunnel, the work I did, the fire design, then you will get a better understanding about the behavior of the material, how they're going to perform with the fire. And the thermal effect. The thermal effect is, of course, you know, we get the sun is rotating around 24 hours, then we got the temperature variation throughout every minute in a day, and the bridges we build is open. It is open to the sun, and then it is quite obvious on the top. You got a radiation, on the bottom you got a shelter, so that difference create it's create the bridge behave in a different way. We're going to understand this one in detail today. So these are the loading you just need to consider when you are designing the bridge. You need to have a better understanding of each and every loading on the bridge, and the construction loading is another thing. But you need to have at least some understanding the way you design the bridge, how you're going to build that one. So these are the construction load effect. I think all of you have seen more than enough for these 4 pictures. The industrial ring road on the Panankau bridge, and the other segmental box girded bridge. I forget the name of this one. I think S3 contract. Yeah, when we were designing the construction, because I put these pictures for you to understand, the gantries is 1,800 ton. This one we put the cranes on the top and a lot of the 66-meter span, but we have a lot of temporary towers. We support the bridge while we are doing post tensioning in here. You can see this is a 229 span main span bridge. We are building using the 100-ton foam travelers, so bridge builders, what we call. So when we were doing this one, because after we finish these bridges, all these bridges will be acting like a continuous span bridges. But during construction, it doesn't happen within a day. It's take like a month and years to build this one. Then, for example, this bridge, it took more than a year to build. So when you start from the pier, the balance cantilever bridge, to until you put the stitch 4 in the middle, you build piece by piece the concrete. If you look at the concrete at the close to the pier head, and the stitch 4, it's got a 1 year difference. Then the properties of the concrete will change significantly over that period. So then the load acting on the bridge will have a significant effect on that bridge. So then to understand this thing, what we do, we do construction staging analysis and the design, and we do time dependent analysis and the design. Now I think you all are lucky, because there are a lot of softwares available to do this analysis, but I would like to recommend you for, like, if you get a time, at least just do a hand calculation, just to appreciate yourself, because otherwise we are becoming more and more like a technology savvy kind of a people, but the just to get a feeling about this thing. But you don't want to get the exact answers, but try to do your simplified models and then try to get a complex analysis, all these softwares performing, give you the answer. And the temporary works and they are loading. The important thing is the bullet, the bullet number 4 in here. When you are developing the bridge design drawing, you will understand this one. I will show you how to develop the drawing. You need to clearly put this assumption and the staging in the drawing. The reason I mentioned to you, because you build the bridge within 3 or 4 years time, you hand over this one, your contractual agreement period will be over 2 years, maybe maximum 5 years. You don't have any responsibility regarding the bridge. So you're going to hand over to the road authorities when they were managing the bridge. And the people, if there's the problem arises during the maintenance or any issue, they should know what are those assumptions, at least. How do they do those things? So all this document is very important. So these load effects, you need to have for the construction load effects, you don't want to have a really extensive understanding, but the rest you should. Any question after these 2 slides? I like you to ask questions, because it's a bit of a, sometime because I'm talking to a computer. Yeah, so therefore I like your feedback, or feel free to ask from, I can't, unfortunately I can't understand or speak in Tamil, but you can ask me in Sinhala, it's okay. Then I will explain you, but in English, because for everyone to understand it. Anyway, so I will then jump into the next slide. So I just put this messy diagrams, kind of a flow chart for you to understand. If you apply a bridge load, because you need to apply the load on the superstructure, how are we going to categorize them? So if you get a bridge, we separate this one into what we call superstructure and substructure. So we knew this stuff. We looked at many times now. When you get a bridge superstructure, okay, we categorize the loading into 3 different groups. One is gravity load, of course. Yeah. And we call the longitudinal load that is on the bridge deck. Longitudinal in the sense the traffic is the bridge we span, most of the bridges, maybe 99.5% of the bridges, we span the bridge in the direction of the traffic, the longitudinal load. And the lateral load, yeah, we separate into 3 different loads. Yeah, this is very, if I just explain you in mathematically, X, Y, Z axis. Yeah, if your X is longitudinal direction, if your Y is transverse direction, your Z is vertical direction. If you go to the gravity load, then the gravity load, we got of course, dead load, superimposed dead load. The water and buoyancy I put under gravity because sometime under the flood. So we just choose the weight, but they are very rare occasion. When we check the bridge, we use that one. Live load, of course, the traffic load is we call live load. For the traffic load is the gravity load. And the other load is the impact load. I think you remember I think the session 2, I talk about the barrier. When the barrier is hitting, there is an effect on when there's the vehicle is hitting the bridge barrier, that will impose the vertical load on the bridge. Yeah, the another thing you saw the pictures like the overhead vehicle sometimes push the bridge up. So there's an impact, the vertical impact on the bridge. You will see this one in detail, not today's session, but the next week. And then if we go to the live load or the traffic load, we got a vehicular load and a pedestrian load, of course. Yeah, we some bridges, we have we call shared path, cycleway and the pedestrian walkways. And some bridges we design only for the pedestrian, not for the traffic, but bridges we design for both. Then we go to a vehicular load. So we categorize them again, a moving load. That means just a normal traffic. Another thing, station road, I think you always experience this one when you are in a traffic jam. There's an alternative loading, but you will come across the alternative loading. I can give you a classic example. While you are driving in a long highway, you feel on a bridge, you feel very tired, you go and crash onto the barrier. So that's the alternative load, one example you can get. The other thing, the heavy vehicle load. So we just use some vehicle to transport big structures like for example, transformers and all other machineries. Then, yeah, these are come under gravity because it's all has a really significantly large the sulfate that create a gravity load. And then we got a longitudinal load. Of course, as I mentioned, the creep shrinkage. This do the job all the time, whether we use the bridge or not. After you build, creep shrinkage and the post tension is always there. And the braking, of course, while you are driving in a car, you accelerate, decelerate, you stop on the bridge. So because of that, there is a braking effect all the time. Because when you brake the car, that inertia force will absorb by the bridge, then the bridge need to accommodate that. In addition to that, thermal effect, because you know that if you heat, it will expand. If the temperature drops, if it is cold, it will contract. So then the expansion and contraction is in there. In addition to that, the effect due to impact, it create a load on the structure. Yeah, because when there is an impact on a barrier, there is a component, because the impact is going to happen. We don't know the impact angle. Then because of that angle, one of the component of the impact will be translated into a longitudinal load. The wind can create a longitudinal load, especially if you are building a long span bridges with the cables, suspension bridges, cable stay bridges, and that sort of bridges. Yeah. If you build some slender bridges across the valleys, the wind can create the longitudinal load. I think last week we talked about, when we were talking about sign structures, you got a wind in perpendicular direction, but your sign structure is going to buffet in about the perpendicular direction. So you might get because of the wind, the longitudinal force. In addition to that, you get a lateral one, of course, due to the centrifugal force. Yeah, when you are driving on a curve, because there's a centrifugal force, that is because you are moving in the longitudinal direction, that is in the perpendicular direction. And the wind, of course, is blowing against the bridge. You get a lateral load, the wind. And the seismic effect, you get the lateral load. Because seismic effect, you will get the longitudinal load as well. And the impact, of course, you get a lateral load. Impact in the sense of collision also included. Yeah. And these are the loads and their application in the superstructure. So when we go to the substructure, all the loads in the superstructure translate into substructure via bearing. So then substructure will get all the loads, the gravity load, everything from superstructure, right? Before we go, that substructure itself got its self-weight, it's got its dead load, superimposed dead load, it's got a lie load effect, all those things, it's got itself, right? You will see this one in the depending on the size of the substructure. Because in addition to that, you get the forces, the self-weight, dead load from the superstructure and the lie load from the superstructure for the gravity part. In addition to that, for the lateral loads, you get the forces translate from your the bearing to the substructure. And then, of course, wind, seismic, water flow, debris, collision, thermal, bearing, earth pressure, lie load surcharge, all are produce lateral loads on the bridge. So, we have a two axis. In any axis, the longitudinal or transverse direction, these load apply on your substructure. So there are the series of loads, you need to combine them to get the critical loads effects. I just put this two slides for you to, when you are designing a bridge, when you are calculating things, for you to make sure that you already capture all these elements in your calculation. You looked at everything and you get a understanding about how these elements are interact with each other. That's why I separate this one into this format for you to get a better picture. Another thing I just want to let you know, because this is most of the things in this one, these are my own way of presenting things. Yeah, so and then the substructure loading, you can see the lateral load, there are more than 10 items that you just need to consider. Yeah. And you can see all the load is transferred from superstructure. I put this symbol, please bear with me. I think I should have explained that when I put SS for superstructure. Yeah, I should have put that one in the, please make a note in your slide. Yeah, the SS mean, what I meant in here is superstructure. I should have to have a note in down here. Yeah, because substructure also you can say SS, but this SS in the sense is superstructure, meaning is superstructure. Yeah, and then if we the next slide, I'm trying to explain to you is about the dead load and superimposed dead load. Is both are the dead load, but why we separate them to superimposed dead load and dead load in the bridge construction? It's any construction, any design, we have this one. I think because most of the design to make it economical, whether it's a concrete or whether steel concrete or any other material, we try to design them as what we call composite material, a composite section to achieve the economy. So I have this one example in here, why we call superimposed dead load in the bridge. In the simple explanation is that the way we build the bridge, we put the pile, column, pier, headstock, and we put the bearing and lay the girders. And then after that, on top of the girders, we build the bridge deck. So when we place the girders and when we place side by side or apart from each other, when we place the deck and the girder will be acting together as a composite section. You can see on the bottom, First we got the girder, and then we put the bridge deck, and then we, after concrete is hardened, we got a nice little closed box section, that is the composite section. So very important to understand these three, the way how it's going to act. When you place the girder, like when you span them, this example you saw the last week is 33 meter span in here. What you got here, your self weight of the girder will carried by this 33 meter span. If the girder weight is uniform, let's say like a 2 ton per a meter length, so then you get a WL squared by 8 bending moment because it's simply supported. So then after that, I'm going to put my deck on here because this is the concrete. It's got a self weight. This girder need to carry that one. The girder need to carry that one. So it's still concrete is wet, but this self weight girder need to carry. Then this self weight of the concrete, I just add onto my girder. So girder need to absorb that load itself. There's no composite action. After we leave it for the 28 days, so for the concrete to gain its full strength, and the girder, the deck slab and the girder will be acting together as a composite. So after we finish the bridge deck, only we do other things. For example, we build barriers. We put our drainage, right, on the side. We're going to put our lighting poles, and then we overlay, we put the asphalt and everything on the bridge. All those things we're going to apply after this concrete section is hardened. So then, in other words, this concrete is hardened. Anything we apply on the bridge deck after the deck is hardened, then we call those loads as superimposed dead load. All right. Then in the bridge, why we so concerned about superimposed dead load? The first, the bridge structures are designed as a composite structures. The construction staging is important. We saw that one now. And the dead load of girders and the deck will be carried by bridge girder only. We saw that. We explain it to you. Any load applied after the deck is hardened is carried by composite section, barriers, asphalt, traffic, miscellaneous loading, etc. I put in here highlight the asphalt, because asphalt what we call the wearing surface or wearing course. This thickness will change over all the time, is overlay over the time. Because of that, nobody can really say the thickness of the asphalt itself is the defined is a fixed number. It's going to vary. So you need to take that one into account when you estimate your weight in the asphalt. In addition to that, I didn't have that picture in here. Girders have a big camber, significantly large camber. For example, this bridge, we can have like up to 60 millimeter camber. When we build the bridge deck in the 30 meter length, that camber will have a significant effect. So you need to put additional concrete to take into account the hogging effect. That is also, it's very difficult to estimate, but you need to guesstimate. Those things you can't estimate. Like if you can easily estimate the weight of this deck, weight of the girder, because those cross sections are well defined. You know the density of the concrete and the barrier, of course. And then you apply the traffic, everything after bridge is finished. So under the composite section. So that's why when we were talk about the superimposed dead load, you need to understand the load, the time when we apply. In addition to that, you need to understand the uncertainties involved with that when you are estimating. For example, if you say in the drawing, the 5 millimeter thick asphalt is on the bridge, you just get the 5 millimeter, sorry, not 50 millimeter thick asphalt. That's the bare minimum we use in the bridge deck. 50 millimeter thick asphalt on the bridge deck. If you just calculate 0.05 times the 22 kilonewton per cubic meter density, and if you design your bridge and then, okay, that is considered as a dead load, that is really wrong. You will see this one later, because when you are during the actual construction, this 5 millimeter thick, 50 millimeter thick asphalt could be 100 sometime. It's depend on the way we're going to build the bridge. These things we need to take into account. The lot of design code itself, it address what we call from the load factors, because uncertainty is higher, we increase the load factor. And then during the analysis and application of the loading, we need to consider the stiffness of the member. For example, when we were just checking the during the construction of the deck, the girder will carry the load. Then you have to use the girder stiffness, for example, to calculate the deflection. But when the concrete is hard, and after that, when you apply the load, so you need to use in your bridge modeling, for example, you mainly model the bridge to understand the load distribution due to the traffic and other loading. So then in your bridge model, you need to use the composite properties in your bridge model. Some softwares are available. You can put this staging, it will calculate it for you. But if you just develop the model by yourself, you need to calculate the composite section properties. I think this is quite obvious. I think most of you understand this one. Any questions? No? So good, Tilina?
All good, Roger.
Okay, thank you. So then I will jump into bridge load types. I think I put this slide last week as well, but I just modify a bit. The bridges, I think we saw the permanent effect, all the dead load and superimposed dead load and is on the bridge. And then the traffic load, because we designed the bridges for traffic. So then other loads come, like a pedestrian maintenance and those load. And then the collision load, it could happen, but not frequent. Impact load on the bridge and the earth pressure, of course, that's inherent with the bridge design, and the earthquake load, and then the water flow. Because the water flow, what we consider is like in the flood event, we are considering extreme event, 1 in 100 year, 1 in 2000 year, but it's all depend on the road agencies and the countries to countries what sort of return interval we're going to use. But we are in extreme events. In the wind, exactly the same. But thermal is happening all the time. So you can see I mark all this one in the red circles. I put here, bridge should be designed for these loads: permanent effect, traffic, and thermal effect. You will see this one. Yeah, because I want to clearly explain it to you. When the people design bridge, they don't understand what sometimes they do. They do mathematical modeling. They just go and combine A, B, C, D, E, F, G, H, plus, minus, this, that. You can develop about 1,000 load case. You say, I design a bridge with 1,000 plus load case and I design it. So when you present to someone this design, there's one person sitting on the other end will ask, can you please explain me, how did you arrive this particular design? What is the basis? Then he will say, oh, in the code, we have this A, B, C, D, E, F, G, H load cases. I got this permutation. You can see how many load case has made any one of these. No. When you are designing a bridge, if you can't explain like that, you should be able to tell the person when you're going to present to them, this is what I designed for. This design is governed by this, and by the other load cases we check. Yeah. For example, if you see the utilization, so if it is 100% utilization in the capacity wise, then from there, if you design your permanent effect and the traffic load and the thermal effect to utilization 95%, most of the time your other load case will be always below 95%. But some instances it will be different. But I'm talking in general. So then the other one with the pink dash line, the bridge design should be checked. When you design these bridges, you should be checked for collision, the flood, wind, earthquake. Yeah, you have to design. And I put the traffic barrier one, yeah, the type F in the black, because this one we mainly design the bridge element, traffic barrier design for impact load. And the other, the one with the red dash, I think the pedestrian load, some bridges you got a pedestrian traffic, some bridges you don't. But if you have them, you have to combine them with your road traffic load. So this is how we have to look at when you're designing a bridge. So another thing you will learn this one, why did I put this slide in here. Why did I separate into this one? You will see when you're going to do bridge modeling. I will give you a classic example. When you are designing a bridge model, when you are building a bridge, right? So we put our file and everything from the ground, because if you just ignore a couple of meters from the ground, the below that one, the lateral stiffness, the ground will provide significant lateral support to our pile, our behavior of the bridge. We can utilize that one. So let's say if there's a massive flood, with the flood, you got a significant cover on your bridge, right? During the flood time, you don't use the bridge. But after if the flood is over, there's some significant cover in your foundation. So you don't have that 6-7 meter soil support, that the lateral support provided by the soil is not there anymore. So, so when you are developing a bridge model, so this, if you design your bridge, because it should be serviceable after flood. So after the flood, you need to check your bridge with this cover effect. So that's what I separate them for this way, for you to understand them without putting everything in the same place and mix it up. So you won't get it. Even the collision, yeah, because you can study them, because the collision is happen not in every bridge. Like if you have something go underneath the vehicle, if your bridge is passing over the roads, so there's a possibility of road collision. So that impact, because this load is significant. If you could remember, that load is as large as 2,700 kilonewton according to Australian standard. It's a significantly large load. 270 ton is a significantly large impact load on your bridge. You just need to check. And the other thing, the earthquake effect, because the earthquake affect the way you're going to include in your model. The load data you just need to include in your model. It's not same as what you are going to do in here. Certain, if you want to change your stiffness in your the members, certain element you can change. So you just need to understand each and every load case and the behavior of your structure. They are not the same. That's what I said. That's what I separate this thing into this element, because later on when you're going to when we talk about the bridge modeling, you need to have this the baseline understanding why we need to think this one as separate. The bridge design is not the combination and permutations. Yeah, it's not you run your, for example, the column design, you just run your interaction diagram and you push thousands of the load cases and you say it's all within that inside the capacity curves, therefore it's working. It's not that. You just need to pick these 3 or 4 load cases, and you need to understand why did I get these 3-4 load cases and why these points are there. You should be able to justify whatever the output from you got from your analysis. This is you need to practice this one, because otherwise I just made this joke with I think when I had a chat with Shiromal, actually if you're going to do everything by computer, we don't want civil engineers. We just need 2 or 3 very good computer engineers, because they can do a better job, because they will codify, they will write a program for the whole code within a couple of months, and then you just input them, they will give you the output. So yeah, you don't want to learn about all those things 4 years in the university. All right. So therefore, you need to take this one very seriously. That's why I just separate these load cases. That's why I combine them together. Because for you to understand clearly, for you to clarify the things in a better way during the latter part of these sessions. Any questions regarding the bridge load? I remember the last week I just, during last session, I just rushed through this one. Any question?
Hello, I'm Dayani. I have a question regarding the load cases actually. So these load cases, is it specified in somewhere, or is it by an experience?
No, is it in the code? Because you can't design anything in engineering by your experience. You use your experience to design the any, but because the designing in the sense is a contractual thing, because you had to follow design guideline, design code. See, all this element is in the design code. They define. You will see later on in the today presentation. They define in the codes. They define in the code in the sense the quantities, how they quantify them. For example, collision load 2,700 kilonewton according to Australian standard. But if you look at the other standard, these values are different. I think, as I mentioned in the session 2 about the traffic barrier, we use the medium performance traffic barrier 600 kilonewton. It has been changed from 500 to 600 in the recent update in the ASP 5100 part, the 2017 upgrade. So this changes, but if you look at the same impact loading in the as another code, they are different. Yeah, it's codified, everything. Yeah.
Okay.
Is that, did I answer you?
Yeah.
Okay, no worries. Thank you. Any other questions? All right, then I will jump into the traffic loading. Yeah, I think we are designing bridge. You should know what is traffic loading, what does this look like, how we're going to use on a bridge, and how we're going to use it. I think, Diane, I think in this next couple of slides, you will understand the questions you ask, get a clear explanation as well. When you want to design a bridge, the next 2-3 slides I'm going to explain, you need to have a really thorough understanding, because as I mentioned in the previous slide, we are designing bridge for traffic load, not for wind load. I repeat this one, we are designing bridge for traffic load, not for wind or earthquake load. So then you should know what is traffic load. You can see the first picture. A traffic on a bridge is a traffic jam. So, no bodies, because it looks like everything looks to me all are small cars, right? So when I'm designing my building, the car park, I design for 5 kPa load, right? Am I right, Tilina? So when you design a car park, we use 5 kPa or different one?
Uh, we use 2.5 for the car parking area, but for the driveway, we use 5.
Okay, yeah. So similarly, this looks like a driveway 5 kPa. So you go to the one on the right-hand side top. It's on a cable stay bridge, the congested truck on a bridge, right? If I just give you one example, you can say average weight of the car is 2 ton, but average weight of the truck is 70 ton, at 35 times higher, right? So when we go to the bottom left, you can see of this Sydney Harbour Bridge. Instead of once in a year, there is a 42-kilometer run or 20 runs, and then this is people are running. It's a massive bridge people use for run. It's for the crowd loading. You have to design the bridge for that loading. Yeah, you know the average person, the weight is 70 ton. I think now in the current trend in the world is 70 ton. Bomb base also is going down, right? It's not looking up, going up. It's not going to go 85, but it's always maybe go to 65. That's the current trend in the world. Yeah, this is a crowd load. And another one you can see on your right-hand bottom, the normal traffic situation. Also looks like there are plenty of space in this bridge, right? So why? So, okay. Then you get a question. If I ask you a question, so which one you going to pick to design the bridge? Yeah, I need answers. You can tell me the one on the top is number 1. No, we will start like the way our X, Y, Z axis. So the first one is the one with the cable stay bridge. Then the bottom is number 2. The other one is number 3. If I split in here X and Y axis, the one on the top left-hand corner is 4. Okay, I need an answer. Someone tell me which one you're going to pick to design a bridge. Huh? And you need to pick, yeah, it doesn't matter. Just this, Yeah, we need to have some fun as well. So which number are you going to pick? 1, 2, 3, or 4? Let's say we design for 3 and we let 1 to go, right? We design for crowd loading and we put the truck on the bridge. Why not? We can, right? Let's say we design for the truck and we put the rest that people say is safe. Why not, right? You see, there is no conclusion. This is not a comparison. Like when you are designing a building or a house, your live load when the I think 1.5 kPa, am I right? 1.5 kPa per square meter. That makes a lot of sense, right? You know, the number of people live, kind of a furniture they're going to have it, because as long as they don't have to have a warehouse in their building. So you got a feeling. But this picture I just put you to understand, there's an extreme ends in a bridge when you build the traffic situation, right? There's no defined way you can say this one is right, this one is not. This is the way we need to design. So I need to pick that one. No, you can't do that, right? Okay. So then we don't know what is the traffic load on the bridge. So I can't decide that one. Then I will go to the next slide. I got a situation like that. So one in the middle, the top, in the middle, you can see that this trailer is transporting a dump truck. This is very common. Wherever you get a construction site, you have this common thing you need to transport. So in a highway, when it's transported, it has to pass through the bridge. So you can see this B double truck, especially in Australia and the other countries, the transportation, the logistic, they use B double truck is very common. And the one on the top left-hand corner is a heavy vehicle. You can see it's a massive machinery they were transporting. And the other one on the other end, you get another really big overheight machine transporting. You can see number of wheels and axle in that one. They are all different. They are all different. You can see one in the bottom, they are transporting a 62.5 ton approximately Super T girder. Yeah. You can see they were transporting this one. To bring this one to the side, they need to bring from the fabrication yard. If I tell you the distance this particular girder travel, it's close to 300 kilometers. Yeah, because we design and build this project. Right? You can see now when you are designing a bridge, right? Your traffic load on the bridge, you can't predict. Remember, we are designing a bridge 100 plus years. I use the word 100 plus years because we had to design a bridge for 120 years. Are we going to have this one almost every day? Of course, we have these trailers going on the bridge almost every day. But in Sri Lanka, maybe at the moment you don't see it, but in the future you will see them, this B double truck. Of course, we need to transport these heavy vehicles as well. If it's a major highway, it's need to cater for this loading. For example, if you get an industrial zone in an area, you need to bring a lot of big machineries and things, you need to transport them. So then you can see your loading pattern from in a bridge for a human being to a car, to a small vehicle, to a big vehicle, to a unimaginable size and weight vehicle, you need to allow to transport in your bridge. For example, especially the construction material, these girders are very heavy. Some girders as heavy as 100 ton. You need to transport them. Then you need to consider when you're designing your bridge in your route, if you allow them to transport, you need to design this one. This is the question now, how are we going to identify which one is the right load to design for the bridge? For example, you can design for the most heaviest one and then the couple of them and put it in there, and you can say, I designed the bridge. I know that if this truck can go on that bridge, anything can go. Yeah, of course. Yeah, then your bridge construction, yeah, you can build, spending that money, you can build maybe 1.5 time longer bridge than what you are supposed to build. Let's say if you going to build 300-meter long bridge, yeah, with that money you can build maybe 450 meters, who knows. Then the traffic loading, to identify, to pick which one is not that easy, right? Let's go to next one. In addition to that, when you put, I think we saw this slide before, when you put the traffic on the bridge, because the traffic is a moving load, the bridge is not that even. I think you got that experience when you are driving through the expansion joint, bang, 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 that noise and that feeling you get yourself when you are sitting on your car. So this dynamic effect will induce additional stresses on the bridge. And this dynamic effect, we need to, because the bridge moving load is a dynamic load, because in the bridge design, we don't use the dynamic analysis, we use static analysis. Then we need to, should be a way to convert this moving effect into a static effect that we combine using dynamic magnification factor. You will see in some code, not some code, Euro code, for example, they included dynamic effect inside their live load, I should say, models. So then this dynamic effect, when you include into a static load, let's say the B double truck, that's 62.5, you can convert into static load. That static load you saw, because of the weight, it give you the axle weight, vertical load, gravity load. Because it's brake, it will give that produce a longitudinal load. And if it is in a curve, you got in addition to that centrifugal load. Yeah. So then, in addition to about all these uncertainties, you have to understand the dynamic impact, dynamic effect on the bridge as well. This is one of the models. There are a lot of research, a lot of things done, but it's very different. Yeah. If you construct a bridge, you know exactly your dynamic effect on this span and next span is never going to be the same. Because, for example, if you, with my experience, so much of precast related construction, you can never predict the precast girder camber. Yeah. You fabricate in the same day, right? Different hours, you get a different cambers. Yeah. You trust me, that is the reality. So you build the bridges, but there are so many uneven surfaces and other thing on the bridge. Because of that, this time dependent vehicle bridge interaction prediction is near impossible. But we get understanding, then we make judgment. I'm sorry, real forgot to explain you something in the previous slide. I have this calculation. Just to give you an idea, like Tilina mentioned, we designed a car park for 2.5 kPa load. Similar to that one, I did a bit of a calculation in here. The B double truck, the weight is 62.5. The length is about 26 meters. I get the total length of the vehicle. Is occupied on the carriageway. The carriageway width is a standard one in a highway is 3.5. It's got a, if you see this one, it's got a 9 axles. From the picture, you can see 3 in the front, then 3 in the dog, in the tail and the dog. Then you got a 9 axle and you got a 34 wheel that produce the reaction. You can see these are the approximate reaction from this particular truck. They are different, they are not the same. And then if you look at the average pressure on the bridge deck, if you divide 62.5 and convert that, multiply by 9.81, then you get a number of kilonewton. If you divide by the area, length is 26, width is 3.5, uniformly distributed, pressure we assume. This works out to be 6.73. Yeah. Makes sense. Okay, 62.5 ton truck. generate only 6.73 kPa. The small car 2.5 or safe, right? You can be now, you can feel comfortable, right? And then I multiply this one by 1.35 to the previous slide. I explained about the dynamic impact. I just increased by 35%. Then I put this number 2 to make sure, because these axle loads are not uniformly distributed load, because I just make a simple analogy. If you get a simply supported beam, uniformly distributed load, the bending moment is WL squared by 8. If you put this total weight right in the middle, it's a WL by 8. I just made that analogy and then I multiply by 2. Still, its work out to be 18.9 kPa, is less than 20. But still, really good. You design a bridge to support this 62.5 ton monster, but still that generate only 20, less than 20 kPa load. Because of that, then when we are designing a bridge, no need to worry, just use 25 kPa or multiply by another factor, just design for 25 kPa, then is good. Actually, it's not going to go that way. I just give you, if you convert this loading in a different way, those analogies is not going to work in the bridge design. Yeah. I just give you this one to get you the about the feeling about this load effect on the bridge in overall, but it's not the way it's performed when we were designing it. So then, if I come back to this slide again a few seconds, because of the dynamic effect, we need to magnify we use the magnification factor to convert that one into a static load. That's what we're going to use in our the bridge modeling and bridge design. This slide is explain you why we need the dynamic magnification factor, how we're going to estimate that one for you to get a feel. Because we are engineers, we should know why we are doing it. The consideration of dynamic response in a bridge, especially we increase there is a stress increase in the bridge. It's quite known fact, because you know that the Tacoma Bridge collapsed, because of this, the stress increase because of the dynamic response. The good example. And when you are driving, if a bridge is vibrate, I mentioned to you this one, I think in my first or second session. So one is moving, other one is on the traffic jam. Is quite common in Bangkok. The people will vibration, they feel discomfort. Then the people in the car, they will feel discomfort. Again, there is a massive psychological effect as well. And if it is we allow the pedestrian to go as well. If a bridge is vibrating, the pedestrian also, they feel discomfort as well. Another thing, especially if a bridge is not uniform, if there's a significantly bad dynamic response from the bridge, like for example, when you are driving through the expansion joint, you know that bang sound, the hammering effect will reduce your design life of your shock absorber. So you need to regularly change that one. The surface irregularities, as I mentioned, camber and deck construction, this is quite common. That's why people use the wearing course, what we call the name. We put that one to make it everything level. We get a smooth surface to drive on. These are some of the factors we we consider when we are looking at the dynamic response. The dynamic response, as you know, I think in the structural dynamics, if a structure is vibrate, if it is vibrate close to the natural frequency, it will amplify, it will get a resonant effect that will make things worse. So this is one of the simple approximation for you to calculate the natural frequency. Phi 2L squared, EI is the rigidity divided by mass, square root of that value. And the I is the moment of inertia. And the M is the mass. So the people did a lot of experiments and a lot of the analytical the research, and they came up with a relationship between the natural frequency against the length of the bridge. It looks like this L to the power minus 0.933. If we say 1, this is 9.4. If you say 100, this is 100 over L, or else LF is equal 100. I think everyone know XY is equal C squared. That is the rectangular hyperbola, right? When you draw this one, it's go to infinity in here. This is the natural frequency. And then if a length is 0, it's infinite here. If length is infinite, that goes to 0. That's how this goes. For different types of bridges, they do a lot of experiment. The types of bridges like concrete bridges, steel bridges, orthotropic deck bridges, all these bridges. I think the researchers noticed this LF relationship is go with the 100, 60, 90, 20, 150, like that. So doing all this research, I think the Ontario Highway Bridge Design Code in Canada, I think they came up with the natural frequency again, the dynamic magnification, how much we're going to use it in the bridge. So this value vary from 0.2 to 0.4. If you look at most of the design standard, that is where we stand. Yeah, the maximum value we use 0.4 in general bridge design, but in other place, yeah, sometimes it's 0.3, 0.33. Yeah, because if you look at the old code like Astro, I remember I used to, when I used the early stage in the 90s, this number, for example, when I used the 50-meter long bridge, I remember the dynamic magnification factor. That is the I think I is equal 1 over L plus 25. Forget the equation is about 0.17. Yeah, the 50-meter long span is less than this value. But the new code is always between these two values. In general, yeah, 0.3, 0.33, and 0.4. Yeah, you will see later on. Yeah, okay. Then now, you know, we got a bridge. We have a different set of loading. We know that when the bridge is, when we are traveling on the bridge, is do all sort of vibration thing. Thanks to people, yeah, before 90s, they did research. They understood this one, because there may be a lot of development after this one, because not like the nowadays, we have a lot of softwares, a lot of capabilities. We can do a lot of things now, better. Now we have a better understanding, but people, we got understanding as an engineers. There's understanding how a vehicle and a bridge work together, how they go together. Yeah. So with that, we can, when we get the dynamic effect, we can convert into a static effect. Yeah, that's the main reason I just want to, I put this slide in here. It's nothing to explain you in theory, just to appreciate. It's not coming out of the blue. It's coming with a reason. Any questions? No? All right. I want you to understand this slide quite clearly. If you understand these 3 slides, you can use the next one, you can use any design standard in the world. It's no problem. I will prove it to you later on, right? I put this one, the traffic load models variables. I put the word variables because everyone can understand. The first dot point, types of moving load on a bridge. Okay, pedestrian, cars, buses, lorries, trucks, heavy vehicle, we show from that one on those pictures. We don't want to talk about anymore. Is a moving vehicle effect on the bridge? Gravity, longitudinal, lateral, fatigue. Yeah, it's in there. When we design, we need to consider. Yeah, especially the fatigue. The word fatigue is very important. Longitudinal load, the braking. Lateral load, okay, the centrifugal. Okay, we need to estimate, right? If you don't know the vehicle, all those things, even the gravity load, they are unknowns, right? How many unknowns in here? How many unknowns in here? All those things, these are not the textbooks. It's everything is from my experience and the way I looked at the thing I present to you. If you go to textbook, you can find so many other elements in there. Another thing, I'm not a traffic engineer as well. There are so many other aspects. We can put it into that one. But I just want you to understand in terms of the bridge design perspective, this one. Vehicle bridge interaction, dynamic behavior. So we knew that it's unpredictable, but still we came to conclusion. The maximum kind of a 40%. That 40% is in the common place, but in the bridge expansion joint, we increased that factor up to 75%. Yeah, and the difficulty to predict varies within the bridge and bridge to bridge. Yeah, now it's clear. Bridge vehicle movement. Yeah, when you are driving, it could be a moving vehicle, it could be a stationary, right? You can drive, you can stop, you can do so many things. You can have a many different speed on the bridge. It's all unvariable. You can't control them, right? You can't control them. They are all unknowns. It's all has to. You have to design your bridge to, you have to get your bridge model, your live load model to accommodate all those things. Bridge types and element, they are different, right? You see eye girder bridges, you see box girder bridges, you see cross beam, you see deck, you see barriers, they're all in there. You have to design all of them. And the bridge design life is 100+ years. I put 100+ and a growth. Yeah, you know, the now with the social media, 1948, what is Sri Lanka looks like, 1900, what is Colombo and Kalpiti looks like, today what it looks like, right? You know that one. So because of that, so we have we were not there, but with those pictures we could understand the changes happen. So then you could understand within the next 100 years after you build the bridge, what sort of things will happen, right? The increased population, number of road users, demand for logistic, also many variables will affect your traffic on the bridge, type of traffic on the bridge, the way the people going to use it is change. Yeah, this is a common sense thing. And the road types, because there are roads on the bridges, on the motorways, bridges on the access road is a quite good example. You all have a bridge on your home, most of you, right? So in your driveway, if maybe go across a small canal, it's a form of bridge. It's an access road. It's a form of bridge. You can have a temporary road for example, for the construction. You can have a rural road for access for the people. Yeah, for example, like in the Australia and like in the Western countries for the massive farmland, we have a rural because we don't get much traffic, but we build access road. But that farmland within 50 years time going to be a massive city. Nobody knows, right? Then rural road, urban road types, motorways, all those things constitute and will give you different impression, but you don't know what is exactly going to happen them over the 100-year design period of the time. And the number of vehicles on the road is quite obvious, right? And the total cost of the bridge as well. I put this one because the bridge design and construction, you can see how much money I want to spend at the beginning. The initial cost, initial investment, because building bridges, the governments are doing, they are investing money. And how much is going to cost for the maintenance and how much is going to cost for the replacement. There is a balance we need to work out in between. That is what we call the value for money in the design world now. So we just need to make sure that we need to take that one into consideration. So this thing will affect, and the enforcement of because sometimes you see some bridges, we say you can't go more than 40 ton, but I know you can't, this a normal 10-wheeler truck is about 32, 33 ton is the allowable load, but people use 40 ton, 50 ton. But how do you enforce that one? So every truck you're going to weigh, and then you have a policeman on the bridge, you can't control. The driver behavior is not controlled. You're supposed to drive on a lane, particular speed is all guided you, but you do different things while you are driving it, right? So you can't control that. The type of vehicle used in region to region, I just put this example. For example, for the transportation mode, in Australia, for example, we use the B triple truck, but still like in Sri Lanka, we use maybe the 10-wheeler and the smaller with the tailors, but it will change it will change within the next 10-15 years, right? So you need to take everything into account when you just selecting your type of the load you have to design your bridge, right? This is some of the examples because it's directly related to bridge design. Another thing you can understand, you always familiar with. That's what I just put this dot point, right? Any question in this slide, right? All right, I will jump into next one there. Then we're going to develop a traffic model now. You saw all these variables right at the beginning, right? And we do data collection. So we do analysis, we do simulation. And from all those things, we engineers, we use the probabilistic approach to make our conclusion. So this is the risk, how we're going to manage. Yeah, we do those things. The traffic engineers and the road agencies, they do this one. They do over the 100+ years. Now we got a lot of fast computers, a lot of softwares, we can do those things. But every day, every year, we're not going to change our design codes, our live load models. Another thing, because when we are designing for new thing, we're not going to neglect our old bridges. We're not going to say, it's not going to work for that time. We're just not going to demolish them and we're not going to build them. We don't have that much of money. So when we collect all this data and when we do all this simulation, the probabilistic model, we develop what we call live load models. These live load models, load effects, we categorize because all the moving vehicle got a wheels and axle, and some design code, they use truck, and some design code, they use UDL. I think the good example, the car park we designed 2.5 and 5 kPa, that example we saw about all these tricky things, it's about 20 kPa, right? Okay, we can get UDL. So we can develop a live load model to use with the combinations, right? So what we can do, sorry, I forgot to switch on my phone. All these the live load models, so we represent wheel load, axle load, truck load, and UDL, right? So then, yeah, that is what we got in a motor vehicle, right? So then, if you go to Australian standard, American standard S2, Canadian standard, Chinese standard, British standard, Euro standard, Indian standard, Japanese standard. Yeah, I'm quite into Australian, American, and the British standard. I had an experience in the Canadian and Japanese standard. All these standards, right? They develop their own approach for to design a brick. They have their own live load models, right? They have their own live load model with reason, right? With reasons. And then these countries, when they develop their standard, this main standard, I think they now around the world, we are using it. The objective is to have though we have a different standard, develop different combinations. When you apply this on a bridge, when you design them, you get not exact outcomes, similar outcome, right? Similar outcome in the sense is safer to drive. This code, when we develop their own live load model for different combination, it should be always interchanged with the variable we looked at before. All these different loading situations, right? Bridge, vehicle interaction, all these unknown thing within next 100 years. What is, for example, simple example, growth of this and what is the traffic behavior on the bridge. All these things need to be represented, but they are not going to be exact, but need to have certain level of confidence for us to design this one. Because of that, around the world, people develop different live load model to design the bridge. While we are going through this over the next couple of sessions, I will explain it to you in detail, the certain aspects some road agencies they put in their mind when they were selecting load cases. For example, I put the one variable, one aspect as the initial cost and the maintenance. And I talk about in the first session about durability of the structures, how we're going to achieve them, right? How we're going to maximize the lifespan of the particular element in the bridge, those considerations. Yeah, they take into account when they develop their own standard, right? But they give you similar outcome. Therefore, I would like to tell you, this is very clearly, when you design a bridge, you should not compare against another design code. They have a different approach, different philosophy. You say, I'm designing for whatever standard, the Australian standard, therefore I'm going to compare this one with American standard, whether C is going to work. No, you can't do that one, right? In the bridge design, you can't do that one, right? If you select this particular design code, you have to follow, you have to adapt to that one. You have to follow all the design guideline given in that code. The reason I need to emphasize this, if you select particular code, for example, in Sri Lanka, you are using Euro code. In Australia, we are using Australian code. This is the priority, but certain design aspects, we need to go to other code because if it is not covered, for example, normal design, no, in general bridge design, all the codes, in general, they write for maximum span 200 meters. If you go beyond that one, I think the ASHTO covers most of the bases. I think then we go there and we refer to that one. Certain element in the bridge design, the people used to refer to ASHTO all the time, for example, the barrier design. It has been the practice here, but it has been changed. But you should not compare the codes to code. This is very important for you to understand, right? If you understand these slides up to here, you should be able to pick a bridge loading on any design code and should be able to apply it, use it and design a bridge. Any question up to now? If you don't understand, I will spend another 10, 15 minutes. I will explain it to you.
Hello, sir. Hello.
Yeah.
So, මට පොඩි ප්‍රශ්නයක් තියෙනවා මේ slide දෙකට විතර කලින් අර මේ පොඩි example එකක් කරේ.
Oh.
අන්න ඒකේ sir කියර මේ dynamic factor කියලා අපි දැන් මේ 1.35 නේ. එතකොට ඒකින් අර value එක ආපු එක ගැන පොඩි ප්‍රශ්නයක් තියෙනවා මට.
නෑ ඒක ගැන ඕක කමක් නෑ. ඔගේ නම ඔගේ නම මොකද කිව්වේ? කමක් නෑ. Okay. It doesn't matter. Like the question is why we use that 1.35 and the magnification factor, right? That is, I just give you an example. That is that we don't want to. That is just an example for just to give you an understanding. When we put a truck load on a bridge on that length, what would be the uniformly distributed area if we do all this very simple calculation. So in the slide, I explain it to you, the dynamic magnification factor, but different design standard is defined what is the relevant magnification factor. Yeah, you don't want to use that one as a baseline. This is just an example. Yeah. Is it clear?
Yes, okay, okay.
All right. Any more questions?
Sir, excuse me. I have one question on the dynamic factors.
Yeah.
Okay. As I know, actually, dynamic effect is higher than the statics effect. So normally the factor is greater than 1.1 is, let's say when we look at the Euro code, 1.2 is a maximum.
No, I think sorry, that is the factor you're going to increase the dynamic load allowance, what we call the technical term. You will see that one. That is, we increase the 0.4 mean 40%, 0.2 mean 20%. Yeah.
Okay. That's what
Yeah. That is the yeah. That's really good. You asked that one because that's the amplification, the amount, the percentage we're going to increase. Yeah.
Thank you.
Thank you. Any more questions? All right, then. I'm going to first explain it to you. What are the live load models, right? We go back to this. We say we're going to use the axles, wheel, UDL, etc. for design bridges. I will give you the first example. I will discuss what is used in Australian standard. Then I'm going to discuss what is we are using in Euro code. So we use the design code, say we use the 80 kilonewton wheel load. It's just one wheel. Come on, you're kidding me, right? You designed a massive, you are talking about 34-wheeler truck over there, or either you are telling us you use 80-ton wheel load to design a bridge. Are you joking or what, right? Yeah. But with this 80-ton wheel load is doing a lot of things. It can be any place in the bridge, right? It's like a dot on your bridge deck, any place, right? When we were designing bridge, sometime this 80-ton kilonewton, this only single wheel, when we design bridge deck, the expansion joint, the abutment, etc., is very important. Yeah, we use it. Because I said, we are developing a model to simulate what is the real effect on the bridge, right? The one is just a single wheel. Other one is a single axle. We call A160. Yeah. This axle mean two wheel. The one wheel is 80 kilonewton. And then there's space. You could see here in this, the red box, the spacing, can you read? Spacing between the wheel is 2 meters. And the size of the tire area is, don't remember this thing and don't worry too much about these numbers. The tire area is 250 millimeters and 400 millimeters. That is the area, the contact area, what we call. And they say this axle is occupied in a lane, 3.2 meters. That means from the center to center between the wheel is 2 meters. From center to the edge of the lane, we call 0.6, 3.2. We call this the standard design lane. This is an imaginary lane. This is not the carriageway. This is not what we got in the road marking, like a shoulder, then the road, the carriageway, and that is not. This is something we use in the design. We call, I think in the Euro code, called notional lanes or standard design lane. And then in the Australian standard, this imaginary lane, they define as a 3.2. And then you put your axle in this imaginary lane. You can draw any number of lane in your bridge deck. You will see in the next slide, right? This is the one form of load model we use in the design. We call A60 axle. Why we are using this A60 axle? When we were designing a bridge, the cantilever sections, the box girder expansion joint, this axle load play a significant part. Sometimes it's govern the design. Yeah. To design all this, a small element in the bridge to make it, to get some worse effects on the bridge, we use this one. And then we call M1600 moving load. I'm really sorry, I should have put this one with the picture. You can see in the M16, M mean moving. 1600 or 1600 mean approximately the 25 meter length. The weight of this structure is 160 ton or 1600 kilonewton, right? You can imagine the before you show, that's what I put that example in there. 26 meter length truck carry only 62.5 ton, but we are designing a bridge with same length, but we are using 116 or 1600 kilonewton weight we are putting in a lane. The width equal to 3.2, actual carriageway is 3.5, right? And then in addition to that, in this one, we have another, the uniformly distributed load, 6 kilonewton per meter or 1.875 square. And this load is consist of combination of axle load and the uniformly distributed load. If I go down to here, you can see this M1600 load configuration. It's got a group of, we call triaxle group, 1, 2, 3, 4. Each axle weigh 120 kilonewton. In other words, 3 axle weigh 360 kilonewton. So we got 4 of them in the bridge, and they were spaced in a way like spacing of the axles first 1.25, then that axle group, the spacing between these two 3.75, one in the front is 5. In between, you can vary whatever the way you want to vary. Minimum 6 to 5, but you can go up to whatever the dimension you 5, 10, 15, 20, 30, any number. We call M is a moving 1600, the defined that 25 meter approximately, the weight is that one to represent. And this one, we increase this static load in the model to represent the dynamic effect by 30%, right? I just have a small calculation in here. M1600, 16,000 kilonewton, dynamic load allowance or dynamic magnification, 30%. That means it's increased by 1.3. In this one, this load is the static load, is in the serviceability limit state. If you want to convert that one into in the Australian standard to ultimate limit state, you multiply this one by 1.8, then 25 meter long, 3.2 meter wide. This particular lane will carry 3,744 kilonewton or approximately 380 ton weight. If I tell you 2 lane is equal to 760 ton, it's little bigger than A380 aircraft weight, because I know that an A380 aircraft got a 24 wheel, every wheel got an axial reaction of 30 kilonewton, 30 ton, 300 kilonewton. Yeah. So this is the most common road, the live load model we use in the bridge design. This is the one of them, M1600. I just want you to understand, you can't compare. You can compare. That 62.5 ton truck, actually that is what is going to happen. And why I am designing this one, then You can imagine the size of the girders, what we are building in Australia, what would be the size of all this beam and thing. Yeah. And still we got only super T girder, 100 millimeter thick web. Yeah. That is not the case. You can't compare these load effects because there are so many reasons we need to have them. That's what I explained that one to you. And then we got a S1600 loading. This loading we represent the traffic jam situation on a bridge. Yeah, it's still the same weight, but because it's a traffic jam, it can have a heavy vehicle, smaller vehicle, combine them together. It's got a 80 kilonewton axle, but it's got a really big uniformly distributed load. This load in here is 1600 loading. Yeah, it's got a really, its axle group are the same, but the weight are different. The position, everything same as M1600. It's got a percentage if you get this one, right? It's 2/3 of this one. And then, but it's uniformly distributed load is higher, or UDL is higher to represent the traffic, the condition in the bridge. You can't ask why we have this number in here. It's very difficult for me to answer, and you should not worried about that one as well. Because I explained it to you, so many reasons we have this conclusion, right? Then these are the two common load case when we were designing the bridge. I think the most common one is M1600 one. If you go to S1600 stationary traffic load in here, because it's a stationary, you should not multiply this one by dynamic load allowance, right? Because this traffic is not moving, right? Yeah, it's stationary. So therefore, you don't want to enhance this one by dynamic magnification factor. So the other one is HLP 320 and HLP 400. Sounds very different. We call HLP mean heavy load platform. The total weight is 3,200 kilonewton and 4,000 kilonewton, right? So we cater this one for a special vehicle, heavy vehicle. If you go to this slide, you can see this one. If you want your bridge to take this one across, you need to design this bridge to one of these load. Yeah, this load got a different configuration, right? The different configuration. You can see the width of this, the bridge, width of this one between the axles in here, we got 2 plus 0.3, 2.6. This one against the lighter one, HLP 3000, HLP 320, 3.6 meters, but the 400 one is a wider the area, right? It could have a more axle, but it represents in different way in this code. Yeah, it's got a 4.5 meter width. It's got a 16 axle. If it is HLP 320, every axle represents 200 kilonewton, one wheel about 100 kilonewton. We see this one got a 4 wheels and it divided by 4. If it is a HLP 400 or 4, that's the total weight is 4,000 kilonewton. So then 4,000 divided by 16 is 250. Yeah, because these are heavy vehicle, they are slow moving vehicle. Because of this, the dynamic magnification, dynamic effect on the bridge is not as bad as normal situation, M1600. Because of that, we use the dynamic magnification factor as a 10%. Yeah, I just did this calc for you in here. 14,000, 4,000 time dynamic magnification factor 1.1 and time to convert this one into ultimate limit state, we multiply by 1.1. then work out to be 6,600 kilonewton. Is more or less equal to 10 times that truck weight, right? 10 times that truck weight, but you can say it will occupy 2 lanes, because the standard lane is 3.2. If you put 2 of them, 4.6.4, I think then this need 4.5 with, it can go in that 2 lane. So if you got a 3-lane bridge, you can put this vehicle in there, you can let that one to go. Yeah. And then, as I mentioned, this A16 axle weight, we use in different locations, especially expansion join the cantilever sections. Then, and this one, we magnify, because this, the load we use to calculate the local effect on the bridge, not the global effect, and it's got a higher dynamic magnification or dynamic load allowance, what we call, we go up to 40%. If I go back to this one in here, so you identify in a bridge design, we separate into mainly 3 load models, M1600, that's very common. S1600, it may govern in a different bridge configuration. For example, sometime when you design a continuous span bridge, yeah. And HLP loading, we call heavy load platform. These load we use to transport heavy vehicles, heavy machineries. And some routes, we don't need to design our bridge to transport this one. But if you design a main highway, it's better to use the heavy platform loading, but this one need to be specified by the road agencies. They need to design for the particular HLP loading, 320 or 400, right? For example, in most of the highways we design, most of the bridges in Australia, we design for HLP 400. So I want to repeat again. You see, we have a wheel, okay? We just put everywhere. We got axle, single axle A160. We have only particular situations we use this one, but when we design commonly, we use M1600 loading. We use the M1600 loading together with X1600, but mostly M1600. And we check our bridges for HLP loading, because these are heavy platform, heavy vehicles, heavy transport is normally is escorted by the police or is guided. It's travel in a particular way. Even if you allow them to use it, this particular operator need to make sure that they need to check the bridge and tell the road agency, yeah, this particular vehicle can transport this one in your bridge, because they need to get a structural engineer assessment to do that. But still, we are designing this one. Yeah, you can see we were in a very complex situation, but when we designed the bridge, we actually end up looking at one single load case. So governing is one single load case. This is true for every design code. Yeah. Any question up to here? Not about these numbers. Why is M1600? Why not become M750? Right? No, because this is what the Australian standard derive for. They got so many reasons, hundreds of years of experience, and so many things put into place. And they have this loading model to design the bridge. Okay, maybe sometimes you don't have a question because it's the Australian standard one. Then I will go to how we're going to position them in a bridge. Because as I mentioned in here, our design lane, axle width is 2 meters, and from axle to the edge of the imaginary lane is 600, total width is 3.2. When we were designing a bridge, we don't worry about the location of the lane. I mentioned the driver behavior one place. Right? There are lanes, but you never, sometimes you don't drive on the lane, you go to the shoulders, right? Because you are driving on the shoulder, that's why you have an impact barrier in there. If you are driving alone all the time, everyone is driving. Like if you got a robotic vehicle, you don't want impact barriers at the end, because it will follow the sensors and it follow the guidance provided along the lane, because the lane marking is there. You drive along that one. But in the bridge, it's not. The humans, we drive. So because of that, this imaginary lane you can place to produce whatever the place you want on the bridge to produce the maximum loading, right? For example, we saw these slides over and over again. This is our traffic barrier in here. From one traffic barrier to, this is a dual carriageway bridge, right? We got a median barrier. This barrier, the distance is 12.5 meters. You can see on the box girder behind, that is 12 meters, right? So when you want to design this bridge, okay, my design lanes is going to occupy between barrier to barrier, of course, yeah. Because as I mentioned, you can drive in between when you design the bridge. You assume people can drive in between, then I'm going to place my imaginary lanes in between, right? So then one way we put that one closer to the barriers. Makes sense, because this is a cantilever structure. You need to put at the end that will produce the maximum bending in the cantilever section, and it produces the maximum torsion in your box girder. In here, we got a barrier here. If you put this one closer to the barrier, your truck or your wheel, you get a really big bending on your exterior girders. Makes sense, right? So you can see in this particular bridge, the width is 12 meter. One is 12.5, the other one, the box girder, is 12. My imaginary design lane is 3.2. Then first thing I will do, I will see how many truck I can put in this particular bridge on this carriageway, inbound or outbound carriageway. Then when I calculate this one, I got a 3 point something number in here. I got a 3.5. Therefore, I said, okay, I will put 3 trucks in here, because I can put another half of the axle in there, because it's the 2.5. I can put another half in there. Yeah, because you know that when you are driving a vehicle, you need the one axle, right? Fourth wheel. So because of that, we're not going to use 3.5. If it is a 3.5, what we're going to use, we can accommodate only 3 vehicles. So we can define only 3 design lanes. All these 2 cases, we get 3 design lane. This one 3 point something, 12.5 work out to be 3.9 something. Still we have a 3 design lane. Okay, then you can see I represent my design lane, the weight, as a truck, as an axle, for you to understand in this cross section, right? All these things I convert into axle, right? And then for you to understand, it's moving along the length of the bridge. So the first truck is T1 in the first design lane, and the second truck is put in the second design lane. Third truck is put in the third design lane. There is some space available. I'm not worried about that, right? And I can run that one along my bridge. So then when I put this T1, we go to this M1600 T1 loading, it's really heavy, right? Then this is my M1600 load on the first lane. Then the another M1600 loading in my second lane, another M1600 loading on the third lane. But I put numbers in here of 1, 0.8 and 0.4. Why? The reason is, as we mentioned, all this model and everything is based on the probabilistic approach. In a particular bridge, different length, because when you design the code, you need to develop the code, the loading system, to design 10 meter, 6 meter long to 300-400 meter long bridges, right? To have this M1600 or massive weight, if I put the word, truck weight in these 3 lanes simultaneously, to have that one is very rare. It won't happen that way. Because of that, the codes say, if you have a first lane, if you have only 1 truck in your bridge, use 100% of that weight. That's why I put 1. If you put the 1 and 2 together, yeah, this it's not happen all the time, right? You can say, okay, I saw in the bridge, 3 B double truck, they were running all together. You saw that is 62.5 or 70 ton, but what I'm designing is significantly large values, right? And then even if you have a 2 design vehicles or M1600 go together, you don't want to use 1 and 1. You use only 80% of that weight in your design. If you combine 3 trucks together, you use only 40% of the M1600 weight to get the effect on the bridge. If you go beyond 3, it's all 40%. We call this one a different, they call the lane load factors, or here we call accompanying load lane factors. They have a different technical terms, but there are different percentage we use. The reason is they are not occurring simultaneously. They're not occurring simultaneously. When you design the bridge, the position of this placing of the truck, you can design, you can place it. I will give you one example. You can see if you put this truck in the exterior end, you agree with me that will produce the significant bending on the exterior girder. Therefore, I should push one truck or truck system to the end, right? And then in addition to that, if you look at this substructure, it's got a cantilever element, right? It's got a cantilever section, it's got a span, it's got a cantilever. If you put more truck towards the cantilever, that produces significant hogging bending moment in your substructure, in your cross beam, right? That's the one way. If you push your load towards right, to the right side, right? If you load the other side as well, you create maximum load within your span in the cross beam, right? Because this reaction will come in down, right? It will make sense. It will position most of the significant portion of the load is in here. Therefore, you produce maximum sagging in your substructure, right? In another case you can look at, if you don't have any load on your right-hand side or outbound lane, or if I call inbound lane, but you put all the loads, the maximum load on the left-hand side, what you are shown in this diagram, it will produce maximum unbalanced moment in your column substructure, that couple, right? So because of that, don't let the computer program to give you all these hundreds of thousands of the loads running on your bridge and decide what is the maximum effect on your bridge. You get the control. You draw a sketches, draw the cross section. Look at, if you position this one in this loading, if you apply in here, it will give more load in here. It will produce that one. Those load cases are sketched down. Put it down in a paper and then give them number, load case 1, 2, 3, 4, 5, 6. Do your analysis, go back to your results, check your number one, you specify this load case will produce the maximum force on your exterior girder, maximum sagging on your cross beam, and maximum out of balance in your foundation. So if you not get that answer, that means you did something really wrong in your model. You need to go back and check it. Yeah. If you let the computer to softwares do marvelous job, will give you results. If you go and design, right? Don't worry about anything, because I believe on my DAS, so I believe on my grillage modeling. I'm very good at that one. Yeah, I got everything right. And you just go and do that one. Then, yeah, you can't design your bridge, because you can develop thousands of load cases, but you know exactly which load case is going to govern this bridge design. That is what at the beginning I said, look at dead load and look at live load on your bridge. You design for that and check for the rest, right? If you understand up to now in this one, I think you know how to design a bridge. Yeah, you know how to design a bridge. Yeah, bridge design is not running a computer program. I have this one all the time. I'm telling the people all the time. You just need to do all these little sketches, because before computer came, the world had one of the best bridge designers. Those bridges are still are surviving. Some bridges as old as 200 years old, right? They all did hand calculation. Yeah, they used their understanding of structural mechanics, and yeah, they all work and they all good. But for you, you got a tools to work. That's your softwares, but you need to control the tools, not the tools control you. That's what I want to repeat. Yeah. Is it clear up to this one? Any questions? If you understand up to this slide, so it's really good. If you don't, please ask the question. So sometimes when you ask the question, it's going to help. Like before, ask the question about dynamic magnification. I clarify. It's help everyone. If you understand this one, yeah, you can use any design code. You will see this one in next couple of slides. You can easily design bridge. The rest is very easy. If you all say yes, then I will jump into next slide, where we use the A16, A160 axle in this situation. You can move this one around in here as well. But when you design the middle section of this box girder, this load won't govern, because your truck will put a heavier load. You can have more truck, because when you design this one, you use only one axle to keep in here. So this one will, with the higher dynamic load magnification, dynamic amplification factor or dynamic load allowance, you get a maximum bending in your cantilever, as well as the, sometimes not the shear, but you get a maximum bending in here. Any questions up to now? No? So good. Then I will go to Eurocode. So I'm not expert in Eurocode, but I try to tell you the Australian standard and European standard, they use different way of things, put different way of express the same thing in very different way, but where they're going to explain is exactly the same, right? The Eurocode, you got a 4 load model. I'm sorry, I just ignore the fatigue design part. The fatigue design, we use the same load model, but only thing, we just going to change the factors, like a dynamic magnification factors and other thing. But in terms of analysis, when you do, it's more or less the same. Therefore, I didn't spend the time to explain the fatigue thing. Load model 1, like in Australian standard M1600, LM1 is the common, the load model we use in the Eurocode design. This is the one. Yeah, this is the one you are using. Yeah, this one, the previous one, you got a triaxial 4 set, but this one is easy. We call the tandem. We got 1 set, 2 axles apart from 1.2 meter, they're closely spaced. But this tandem, they give you not 1 traffic model, they give you a 3 design lanes in this model. It's a well defined, not 3, more than that actually, for the whole bridge. And the difference in here, you don't want to compare the axle space in 2 meter, but the lane width from edge to the center line of the axle to the imaginary lane. Previous one we call design lane. In this the European standard. I think the British standard is called notional lane. I think that mean is the imaginary. This imaginary lane or design lane is 3 meter. Yeah, it's 3 meter, a little less. It's 3 meter, right? If you look at the way they put this one axle, is multiplied by the axle load they represent by QI, QK, I is the lane number, highly mathematical, forget about all this I thing. And they represent the first lane in the axle, 300 kilonewton, the tandem is 600 kilonewton. You put a 600 kilonewton, because this closed space 1.2 in your lane. You imagine if you got a 25 meter span or 30 meter span load, you just put your axle load right in the middle. That will give you PL over 4. PL over 4 bending moment are significantly large. They define not the UDL, the load defined as a pressure, the kPa. The first lane, the pressure is 9 kPa. If you convert that one, if you multiply the lane with this 3, if you create like a UDL, that is 27 kilonewton per meter. You can't compare. The previous one, you can see heavy axles, but light lane load. But this one, the axle is light, but your UDL is heavy. You can't compare, that's what I said, right? In this one, you got a first lane is heavy. 600 total axle weight and the 27 kilonewton per meter UDL. When you go to second one, the court say use the second one, the axle weight is 200 and the total weight is 400, and your UDL, you just push this down from the kPa from 9 to 2.5, that's equivalent to 7.5. And the third one, if you go reduce to 100 and 2.5, you can see the tandem, the axle weight, I put the num 1, this is 2/3, is 1/3. It makes sense that 1.8.4, I make this occurrence, it's not simultaneous. The probability is very low. Because of that, they change this one. And you get a higher UDL, but lacks axle load, but this one is much easier to use compared to the, in modeling terms, even you can use hand calculation to do the bridge design using Euro code. If I conclude this one, we got a concentrate and uniformly distributed load. You got a tandem, 2 axles, 1 axle weight 300, 200 and 100 kilonewton. You got a UDL, it's vary 9 kPa to 2.5 kPa. The axle spacing is in the tandem is 1.2, and the wheel spacing is 2 meter, but your notional lane or your design lane width is 3 meter. And there is a multiplication factor alpha time because they put this one. This code is defined in Europe in many different countries, and their road agencies can define this factor. You want to multiply by 10% or you want to reduce by 10%, or you want to use it in a rural area, you want to use the factor what 0.6, or if you want to use in the if you want to use the same one in the highway, you want to use what. So if you want to use this one in a port like an industrial area, you can change these factors. But the code says if you don't have any specific numbers from your road agency or in the national annexures, you can use number equal to 1. I use the 1 in here. In this particular one, dynamic amplification is already included in the design. So you don't want to worry about this one. This, whatever the output you already get in this analysis, this will give you the SLS loading. As I mentioned before, I'm not the expert in this code. And if I am not correct, someone need to correct me with some bridge experience. And then the this is the common load model. I put that one in the bridge design. And if you can simplify it by combine the axles by, but I don't recommend that one. Yeah, this is a very simple load model to use it. Then I will go to the example we discussed before. The distance between our barriers in the bridge barriers in the previous one, 12 and 12.5. Before, our width of the design lane is 3.2, but in this case 3 meters. Then if you divide this one by our number of design lanes or notional lanes, if you calculate this one, it's worked out to be 4. If you go to this load model, your 4th lane in the design, so that at any value is equivalent to design a car park in a building. 2.5 kPa. That's exactly what we are talking. If your design lane, if you got a 5 lane or 6 lane, 6 lane in the bridge, 6 lane in the bridge. If you get a 6 lane in your bridge, but you can see the first 3 lane is the one is governing. The rest is, yeah, it's a 2.5 kPa. It doesn't add significant load onto your bridge. This is what you're going to use when you are designing, for example, in Sri Lanka. Any question about this, the load model? As I mentioned to you, there is no difference between the design code. They represent in the same way. LM1 is your design load model in Eurocode. Yeah, you can use it. Right. This is the load model. Load model you're going to use when you're designing using the Eurocode. Any questions? Come on, you need to have a question in this one. No questions? All right. Give me 10 seconds. Sorry, guys. Sorry. Do you have any question about LM1 model? No? Yeah. LM2. It's the same, single axle, the same concept, but only thing, this one is quite heavy. This is the 400 kilonewton. Another thing, if you look at this figure in here, this axle spacing is 2. Yeah, because they won't change because axle spacing is 2. But the wheel tire area, they change it to 0.35 to 0.6. And this, you can see this hatch line, they put number 1. You can get your axle against the barrier. You can see this, the box girder cantilever section. You place your axle against the barrier. Your tire can contact the barrier face. So that means this, the width of the tire area is 0.6. That means 0.3 from the, if you use the point load, 0.3 from the face of the barrier. You can see this one will produce significantly large the cantilever bending in your slab. Significantly large bending in your slab. That doesn't mean if you are using Eurocode, if you design, and it has to be because Australian standard is 160, Euro standard is 160 mean 80 kilonewton against 200 kilonewton, 2.5 times higher. Because of that, I need to have a larger section, need to be increased the reinforcement. That proportion, no, it's not right. So you have to do your modeling, your analysis to get that from the distribution load around in the global way. It's very different, right? Again, I put these factors equal to 1 and dynamic no dynamic amplification required, is already included. Used for mainly, we can use for the deck analysis, cantilever section, expansion joint. Please note that when you expansion joint, as I mentioned in the Australian standard, the normal is 30 point, magnification factor is 30%, but when you design the expansion joint, is go up to as large as 75%. So the this particular clause will define you what is the magnification factor required when you design expansion joint. But normally bridge, you don't design expansion joint. I think it's designed by, it's a proprietary product. It's more designed by the suppliers, but you can, if you want to check your design, their designs, yeah, it's better to keep that one in mind. This is the LM2, is very similar to A160, right? These two, you can see the similarities. Then the third one is LM3. The LM3 is the load case they define for special vehicles, heavy vehicles. Yeah, they're designed for heavy vehicles. And you can see the similarities. The Euro code, because the it's a continent you design for, and the various roads, types, locations, they use various kind of heavy vehicles to cater that one. They define to smallest to largest. The smallest is the heavy vehicle, the category, they identify 600 kilonewton against 3,600 kilonewton. Different approaches in different countries. Don't compare. Please don't compare. And they again give the number of axles, and they are spacing 1.5 meter spacing, right? The width of this vehicle, if it is a light vehicle, you can see 600 to 1,800. Or axle, the weight or the wheel load is less, then they use a smaller weight, right? Axle weight 150 kilonewton to 200 kilonewton. You use this diagram in your, yeah, it's like a 4-wheel kind of a thing. And 2.7 meter width in your special vehicle. But if you go to heavy one with the heavy axle load, 240 kilonewton one, and the number of axles is 10, maybe 12, or maybe 15, or combination of this, the width of the bridge, the width of the vehicle is wider, is 4.2, because you have a more wheels, right? This, for example, is not the 4-wheel, and this one instead of 6-way. And the code says special vehicle is slow moving, is always with you have an X code when you are transporting this thing. You don't want to use the DAP, the dynamic amplification or dynamic load allowance. You don't want to use it. This one can combine with LM1. Of course, in the other standard as well, you can do. And this one is specified by the road agencies or otherwise as designed, because of this one especially, when you are going to use in Eurocode, the road agencies need to, I think they are contractually bound for this one. They need to design, they need to define what is their requirement for this particular highway or particular bridge. If they want to design the bridge designer to design their bridge for a heavy vehicle load, then they need to specify what is the LM3 model. It could be 600 or it could be 3,600. Any question? No? Then you can see if you use the lighter wheel load, axle load 150 to 200, because the width of the defined imaginary vehicle is 2.7, then you can occupy that one in your notional lane or your design lane, 3 meter. When you have this one in here, in the 2, this is the lane model LM1, the one you specify to, that is the, I think, a 200 or 400 kilonewton tandem load in here. If your if you go to higher axle weight or your vehicle width is 420, then you need to occupy by the two design lanes, because the width is 4.2. Two design imaginary lanes is 4.6. So normally in the bridge design, for example, in Australia, we normally define location of this heavy vehicle when we transport. So normally it's the center line of the carriageway. We just mark in the bridge drawing. You will learn later. That's where they need to drive. It's like the airplane. So you define because it's a escort, because they drive slowly. They can manage that one. They said this is where you need to drive. Yeah. And then accompanying the other traffic within that one is all depend. If you get a 25-meter long bridge, if you get a 1 kilometer long bridge, these are two different situations. It's all road agencies can specify. Like they say it's a 25-meter bridge, you don't want to worry about when you design for heavy vehicle load the other vehicle on the 4-lane bridge, the rest of the area, because it's a short period of time, short length. Yeah, but if you are designing in a highway project, infrastructure project is a couple of kilometers in length, you can't say my bridge number 1 is this one, bridge number 2 is that, bridge number 3 like that. You can't do. You need to have the standard way to design that one. You specify this particular heavy vehicle one, for example, 3000 kilonewton, a special vehicle, LM3. You should consider in your design. This is my preference. You need to design your bridge for that one. So you can see there is another vehicle load in there. That is the LM4. That's a crowd loading. That's the 5 kPa. That's quite a standard one we use in the bridge design. Yeah, it's combined with the LM1 or any other load. Yeah, in that one, in terms of the road design, doesn't cover. If you understand up to this slide, but I explained it today, close to 2.5 hours. Yeah, if I ask you to design a bridge tomorrow, yeah, you may model your bridge in a wrong way, but if I ask you model the bridge tomorrow in a superstructure and give me the bending moment, shear force, the torsion, what we are designing, any structural element, right? You can do it if you understand up to now. If you do not, please tell me, I will explain it to you again. Because this is the landing. In our staircase, we're climbing up. You should not climb up if you're not clear up to now. Yeah. I spent 11.5 hours altogether in this whole the sessions, but so one of the most important thing I explain you is the last couple of slides. I give you an idea why when we were designing bridge, so many things we had to assume this, that, but you can see the design codes make our life very easy. When you design based on the Australian standard M1600, when you design using Euro code is LM1. Yeah. Yeah. This is not theories. This is real because I design enough bridge to tell you this one. Yeah. And I don't want to design using Euro code to explain it to you then. Again, to design for your bridge, design for your traffic, that is Euro code load model LM1. But if government agencies ask you to check your bridge for LM2, you check your bridge for that. Yeah. If there's an issue, you can convey that one back to the road agency as well, rather than upsizing, because this could happen once or twice throughout the bridge design life. And instead of going 3,600, they can scale down to 3,000 kilonewton if it is working that way. We are engineers. We have to make our judgment with reason. We are not mathematicians, and we are not doing computer programming software kind of thing, because you input, you get output, another one. No, we are, because they're spending so much of hours to understand this and program that one to make everything comfortable. But when you design bridge, you can't do that one. As I explained in this slide in here, you put the loading in this bridge, you should have to have your own diagram. You need to have your own imaginary bending moment diagram, and you need to mark those values, and you need to specify these load cases 1, 2, 3, 4, 5, 6. I don't want more than that. And then you go there and you check your results. You don't want to go hundreds of thousands of load case produce and what we call the envelopes. You don't want to go to the envelope. You just go there and then just check your load case first, and you will see that one will supposed to be on the top of your envelope. The rest will be underneath that one. If no questions, it's all clear, then I will go back to the rest. They are pretty easy. Yeah, they are pretty much easy. And even if you read the slide, you can understand. The braking loads on the bridge. Of course, when you are driving, we brake the load, right? But the numbers, the different code, different numbers in Australian standard. If you use a single design lane or single imaginary truck in your design, they said you are depending on your size of the length of the bridge, right? Your braking load can go as large as 720 kilonewton. Yeah, the maximum value is 720 kilonewton. And our example, this one we can put 3 lane in this bridge, right? Then it's not single lane, it's a multi-lane. Then the code say if you use multi-lane, it's depend on the bridge length. Your calculation is based on different approach. The braking load is the 15% of your total weight of the structure. Total weight of your traffic load. What I mean traffic load, this design load. And the previous one, if you use a single truck, you use 45% of that weight. It's really significantly large. You can see your truck weight is 62.5 or 70 ton. Your maximum braking load itself is equal to 75 ton, 72 ton. The weight of that truck. You can do a simple maths. You can do the, while you are driving 100 kilometers per hour, equal to 28 meters per second, your mass of the structure, 70 ton. So then it's brake on the spot within 2 seconds, 3 seconds. During that time, what is the deceleration? So what is the weight? You multiply the mass time, the deceleration. So you get the braking load. That's the Newton's second law, F equal ma. So you can calculate that. Yeah, this is significantly large. You will see it's going to impact your bridge behavior, this force, right? There is no comparison. Yeah, there's a reason to do that one. Maybe you will understand this one like in the latter part of this presentation series. We got the 15%, but it's limited to maximum 1,200 kilonewtons, 120 tons. It's significantly large. Yeah. And then we got the 15%, and then they say, get the total weight of the traffic load. Yeah. So total weight in the sense when we were getting the total weight, we get the contribution. First truck 100%, second one 80%, third one 40%. But just to refresh your memories, in Eurocode is already defined. In Eurocode, dynamic amplification factor is already included. It's much easier, straightforward. But when you calculate the braking load, there is no dynamic amplification required. Yeah, load shall be applied according to the distribution. You will see in the picture, I will later explain, but this is not a must when you design in the bridge. Yeah, only special occasions you need to do. For example, in my background, if you design that bridge, yeah, this statement will will sometime affect. Any question in here? It's a very straightforward thing. You calculate the total weight and get the, yeah, you know, the M1600 load, 360 times 4, 6 times whatever the length of the bridge. Yeah, we will see an example later on. Any questions? Yeah. And the braking load, when you apply, load shall apply according to the distribution. If you design this bridge, the continuous span post-tension bridge, it will take a nicer spiral curve. So this is the 50 meters in height. This braking load along that one, this is along the center line of the bridge. You just draw around in here. That's got a really good path. You can see if you put this axle there in a different location, so that will have a significant effect in your bridge. If you use the computer model, you can simulate this braking load as a moving load and you can get your effect. Otherwise, you have to make your own engineering judgment, developing different load cases to in that one. Even this bridge is a continuous span box girder bridge. Yeah, the positions will affect the behavior of the bridge. The reason is the column height has a significant variation along the depth because of that. The braking load is along the longitudinal direction or along the traffic, which makes sense. And then the one in the perpendicular is centrifugal force. For you to understand the load apply in the M1600 location, I just draw this FB1 in the force braking 111 because I put 1 because it's the same axle weight. Then if you get the same percentage, you get a same load in here. Yeah, but in general, most of the bridges, you just apply this one as a 1 load. You will see this one in the other slide later on. Any question up to here? Is it clear? Okay, go to the next one then. When you apply the braking load on a bridge, the length of the bridge is 600 meters, 600 plus meters, I should say. The distance between the expansion joint is 204 meters. I have this picture on your left-hand side. You can see at EJ in expansion joint, a gap. I just blocked that one now. The reason is when you brake on the bridge, when there is a gap, so it's the force is not going to pass from that point to the other point, unless otherwise you brake right on top of the expansion joint, right? If you brake any other place on the bridge, right, it's not going to go across the gap. Because of that, when we design for the braking, we need to consider not the total length of the bridge. We just consider the segment that located between the expansion joints. The distance between the expansion joint of this bridge is 204. Now what we try to do in this particular bridge, we're going to calculate what is happening with the braking. First, we need to calculate the braking load. To do that, I just need to, because we know the braking load is a function of total weight of the our design truck weight, then I should know first step, how many trucks I can put in this bridge on this side. Another thing I forgot to tell you, when you analyzing even inbound, outbound, dual carriageway, in terms of the braking, we get only unidirectional. It's not, yeah, one might say you are accelerating that one. It's got a traction because you are decelerating on other direction. Because of that, you got a braking, but they are in both direction, acceleration and deceleration in vectors. So you got a force in the same direction, you double up. No, we don't do that, right? We don't design the bridge like that. The code says, yeah, you don't want to do, just consider the one side. That's what I have this loading on the one side, the same example. Because this Australian standard, because of 3 trucks in this our example, the contribution is 100%, 80%, and 40%. So the length of the bridge is 204. We know number of lanes. So we know if you put all this lane, 1.8 and 0.4 equivalent to 2.2, equivalent M16, one truck. So if I calculate the total weight of that one M16 truck, This truck got only triaxial force set, 360 into 4. And it's got a 6 kilonewton meter load. The length of the bridge is 204. Then if you work out to be 2,664 kilonewton. Because it's the multiple, we use the multi-lay, we consider in our design. So then we have to multiply this, the total weight is 2.2 times, I think I made a mistake in here. It's supposed to be 2,000, not 760, please correct. 2,664 in here, please correct that one. This total weight time, the codes say you use the 15% of that value, is work out to be 879. The thing I wanted to point out to you, if you use the same bridge single lane, that will give you equivalent 720 kilonewton. You put all this loading in here, your braking force is not going to go up that way. Yeah. But if you look at in terms of the bridge, you always need to check in your bridge design, single lane effect, because you are going to put that one at the right at the corner. Right? Because if you design a building, you know that if you just apply the wind create the like suction and compression on either side, it will create the kind of the rotation of your flow, similar to that one. The bridge deck can twist. Yeah, you need to check that. Yeah, and 2 is heavy and everything. We work out to be 879, right? The reason is all these things, as we mentioned, is the probabilistic modeling and approach. So the calculation of the braking load, not that difficult. You can do it very clearly, spell out in the codes. So then I put this one in the bridge. This bridge, it's got a 12 girders, right? And 6 span. This 204 meter expansion joint to expansion joint cover 6 span. I think this is that the one we talk about, 34.1 meter span bridge. That example I discussed last time about the ULS capacities. Then 6 span. So we got how many girders? Because we are looking at the half of the bridge, because then this bridge have a joint in the middle. 6 span, we got a 72 elastomeric bearing, because every girder we have a 2 bearing, right? Then 6 into 12, we got a 72 bearing. And the deck, when you apply, because sitting on the bearing is like a floating, it's like a, you're putting on the, not sure whether you can see, it's like a A4 paper. It's sitting here on the elastomeric bearing is a rubber. When you apply the horizontal force, the bearing will shear. Because of the shear deformation, the bridge deck is very stiff compared to the stiffness of the relative stiffness of the bearing. It will move like a rigid body, similar to when we were doing the high-rise building model. Your flow behave like a rigid body, right? So then the rigid body movement, the applied braking force resists by the shear stiffness of 72 bearings, and the bridge will push like a rigid body. You can see this red line, it shows the deformation. The abutment side, the direction of braking from away from the abutment, then the bridge will move to the front by 56 millimeter. These numbers are here. Yeah, this right numbers, 56 millimeters, your bridge will move. This is very different. If you design this one with the pot bearing in the other form, your bridge articulation will decide that one. Yeah, in this particular bridge, sitting on elastomeric bearing. Yeah, and this shear stiffness, because of that force transfer across the bridge, that will translate back to substructure. Then substructure will deform, and that will add on to the bridge. that will add on to the bridge by another delta amount. Then the total movement of the bridge, not the bridge movement, global movement of the bridge, not the relative movement, global movement of the bridge will be little higher because your abutment is bit stiff compared to the bridge piers. Then you have a little bit higher, couple of millimeters add. So sometimes the structural engineers, I noticed the people were arguing about this 2-3 millimeter. You didn't consider the substructure deformation. That one is so big. That is going to have significant effect because they never do bridge analysis and the design, how significant that number is going to be, and they keep arguing. There's a effect that not that significant. It's very different if you use the fix port bearing in a box girder bridges. That is a different story. And then this movement in the substructure, because the load transfer, you see, this 879 move across 6 portals and 12 piers. 12, because this portal got a 2 piers, 12 piers. And every pier, if you got a minimum 2 piles, then how many piles? 24 piles. It's a lot. That load distribute. You can see that if you divide this 879 divided by 24, you can see amount of shear you're going to apply on top of your pile significantly less. Yeah, this is what you need to do when you design bridges. Let the computer to do that job, but do your part. Just do all this a small calc, get your numbers. When you model, when you look at your shear force, calculate those numbers, do a cross check. Do the cross checks and see the relative deformation of the structure. You will see in the next lecture when we talk about bridge articulation from the movement, elastomeric bearing, you can exactly say what is the force on your substructure, how much is going to transfer by the frame, how much shear your pile is going to get, your pier is going to get. Yeah, you just need to calculate this one. Yeah, when I say the rigid, the movement, that one will be 1 or 2 millimeters on the either side will be changed, but in general, it will move like a rigid element. This is true for any code you use, any analysis you use, because you use different code. The only difference is this FBS is a different value. Then this 56 millimeter is a different value, but you may get the same 56 millimeter. You may use different bearing. Yeah, you can fix 56. You change reduce the stiffness of the bearing. Yeah, you can play with that. Reduce the stiffness, or mean you can reduce the thickness of the bearing. You will learn this one later. Any questions up to now? If not, okay, I will quickly jump into the next one. The centrifugal force. Yeah, again, this is you study in your A level. MV is squared divided by R, right? In this case, V squared over R, WC over G. This makes sense because WC is in kilonewton. You need to divide it by G, gravitational acceleration, to make this one M. It's the same equation, right? You just calculate, right? The only difference is it says this factor. You can't just keep going that one. This factor you control. The maximum is 0.35 times super elevation, the theta angle super elevation. You learn in your high school. I don't know the current generation, they know that one, but when we were students, we learned about this one in your applied mathematics in our A-level class, right? And when the car is moving around in a curve, there is a centrifugal force is pushing away to the counterweight of the car. You can get the advantage is that is pulling towards the center of the circle. So if you keep changing the super elevation, like if the tighter the curve, the road designer will come up with the higher the super elevation. You can see this theta is negative, then this number is getting less, then this maximum value is getting less when you increase the radius. I did the quick calculation for the same example we talk about. The the definitions are the same. The WC, V is the speed in meters per second, R is the radius of the curvature. It's that you can get the in the center line of the bridge. If you use different lanes, some designers use the average center line of your, because you have multiple lanes. Some designers use each and every lane, that center. They got a bit more accuracy. It's up to you to decide. You can calculate your R. For the same example, you get 3-lane bridge. I say that radius of curvature of that bridge is 800 meters. The speed of the normal speed of the highways in here is 100 kilometers per hour, equivalent to 27.8 meters per second. You know, G is 9.81. So then the total weight, when we calculate our M1600 imaginary vehicle, is the M1600 time the other 2 lane contribution, altogether 2.2. Then we got 5,861 total weight. So when we use this equation, if a super elevation is 2%, then if you use the maximum break-in load, if you calculate, that is 0.35 minus 0.2, that means 33% time that total weight. That is what this equation says. That's work out to be 1,934 kilonewton, as significantly large. That's the maximum is you can go up to, but this particular radius, if you calculate this, the centrifugal force is about not 33%, it's about 10%. It's equal to 577 kilonewton. And this one, you can see I just do a bit of a the calculation. If the radius is close to 250, then it will reach the maximum, the load, maximum load, but you can get based on this as a centrifugal load. Don't worry about this last statement, but you can easily calculate. It's about 10% for 800. But if your radius is less, you know that it will proportionately increase. So you can easily calculate that one. So similar to the braking load, you can apply your braking force if you need as a one load, or you can, if you want to more accurate analysis or to design check, you can act in your axle location. But I recommend you to apply that one as a one load, one braking load, one centrifugal force together. They are perpendicular, one in longitudinal, another one in transverse direction. Similarly, Eurocode define the braking loads between the 0.6 to Q came in, because in the tandem we got the 2 axles, and 10% of the uniformly the pressure. So that I developed for load LM1 case, the lane 1, you got a 60% of the total axis 600 time 10% of the 9 kPa, lane width is 3 meter, 27 kilonewton per meter. You got this linear equation 360 plus 2.7 L. Lane 2, similarly, because your axle is weight is not 600, it's becoming 400. Your line load is not 9, is 2.5 multiplied by 3, 7.5. That's 10% of that, 0.75. Then the lane 3, again the axle reduced to 200, then it's 120.75 L. So if you combine these 3 lanes together, then you get the total. In that our example, all 3 together 720 times 4.2 L. This is a linear variation. It's very easy to calculate. Then the 3-lane bridge, right? Because your axle spacing is 1.2, that is the minimum length of the bridge. If you consider, you get 7 to 26 minimum braking load on your bridge in this lane. The length is only 1.2 meter, right? That's the minimum you get. And if you get your bridge more than 43 in this 3-lane bridge, you already reach maximum. The code allow is 900 kilonewton. the code give you 900 kilonewton. So if you consider only 2 lane, it's very easy to use this one. Your lane will be 87 meters. If you use a single lane, go to the ML1 on the single lane road. This code normally designed for 200 meter maximum length is represent that one in this 900 kilonewton. So your braking load will be applied on the traffic direction and it's on the longitudinal axis. In the transverse axis, you get a centrifugal force. In Euro code, they have this one, what they call, because they say when the people are driving, they not brake parallel to the traffic longitudinal direction. It may be slightly, because it can slip, because different, especially the winter time and other time, it can slip. So you need to consider 25% of the contribution. This normally what we covered in the design code, what we call the lateral restraint system. Any bridge we design for 500 minimum lateral restraint load. That's covered already in there. But for your understanding, I put that 25% of that braking load consider as a skid load in the transverse direction, because 180 to 900 is very easy for you to calculate. The variation is between 45 to 225, but it's normally we design bridge for that one, even without, even if a straight bridge, still we design for lateral restraint of 500 kilonewton. But if it is not specified in the design codes, you have to design at least this one based on the braking force, irrespective of the curvature, right? Any question about braking load? Any questions? Okay. Then centrifugal force. The Euro code is very straightforward, it's very easy. If it is a centrifugal force, if a radius is less than 200, they say use 20% of the tandem weight. That is 20% of 600. That's equal to 240, right? And then if it is between 200 and 1500 radius, you use this equation. It's a 0.2 is varied to 0. This is the graph, the linearly is going down. So you can see if you use that 3-lane example in here, that's what I draw in this diagram, 3-lane example in here, right? Then your total weight is 600, 400, 200, 1200, 20% of that one is 240 kilonewton. Your maximum centrifugal load is 240 kilonewton, and it will go down to 0 with the radius. Yeah, the radius is 1500. It's becoming 0 because you don't want to consider any centrifugal force. They're very, very straightforward to calculate. 240 maximum and the other values in between. Any questions in here? No? Okay, thank you then. The pressure from the traffic load. This is just when you're designing approach slab. This is the one example, approach slab design on a bridge. It's vary from bridge to bridge, especially the ground condition to ground condition. We have to come up with many different solutions. I'm just giving you one standard, one example. We try to get what we call the live load surcharge on the bridge, because when the truck is or the traffic is entering into the bridge, where it has to go pass through the abutment, normally we have approach slabs in there, so that when we put the truck load on the approach slab in here, right, that approach slab will translate that load into the push the soil underneath. This vertical pressure will create a horizontal pressure on your abutment wall, abutment structure. So in general, the abutment structures, you can see this abutment structure significantly large. Structure is about 3.2 meters high, but in between, in the traffic direction, you have a, to make, to batter, bridge batter to work, you have a wing walls around there, and then you got a compacted soil, and then you have an approach slab on the top. So your traffic within this approach slab will provide the pressure underneath the approach slab that will produce the pressure on the soil, and that translate into the pressure onto the horizontal pressure. The vertical pressure translate into horizontal pressure, you know, the active and passive pressure, active pressure onto the abutment wall. So the in the Australian standard, I didn't put that one on in the what is in the Euro standard. I think it's straightforward. You can read through that one. In Australian standard, they say you consider this one. The bridge approach abutment is equivalent to 20 kPa. Heavy weight, but 20 kPa. Why is it? I will explain it to you. Because this the load we are putting on top of the approach slab. This slab is about 350 meter thick. So then, if you want, you can do a plate sitting on a spring. I just give you this number: well compacted soil. The subgrade modulus is about 60 MPa per or 60,000 kilonewton per meter cube. Or you can ask one of your geotechnical engineers to give you that value. So using this spring constant, you can analyze this one, and then you can calculate the pressure. If you do a simple plate model, you can calculate the pressure distribution, the average pressure distribution underneath on your soil on the top, and then you can get the pressure distribution below using the analysis or using empirical methods. Or else you can use, it's given in the code, the first 3 meters, you assume the behavior is uniform. And then beyond that one, from 3 meters to 8 meters, you assume is uniformly die out, right? It's a 0.2% gradient. Or else if you want to do your own analysis, you own calculations, you can do your wheel load based on the wheel spacing. This is this approach, I put it in here. If you're designing a rail bridge, you need to have this approach. You can get the distribution within the concrete 1-to-1, within the soil 1 vertical to 0.6 horizontal. Then you can calculate the pressure distribution, and then you can get the vertical pressure distribution. You can translate, multiplying that one approximately time Ka, active earth pressure coefficient. So if you get like a well compacted soil, the phi dash value is close to 28 degrees. That is equivalent to 0.37 something, close to 0.37 Ka value. You can calculate the pressure distribution based on that. Even if you apply uniform pressure distribution, it still is work. The AS5100 give quite descriptive way to calculate this one, because if you just use the one wheel or a group of wheel together, you can calculate your pressure distribution, because the wheel lie in the model 2 meter spacing and 1.25 meter spacing. They were closely spaced. Because of that, there will be some overlapping, but it's still, in terms of the design, you can get this one together and uniformly distributed pressure you can assume, and you can design. I think that doesn't make a significant difference in your substructure or your abutment design. So you can have a very accurate the approach, or you can simply use the code, or you can ask your geotechnical friends. They can model this thing using geotechnical software, so Fluxys, or even if you use the like a strand 7, you can model the soil and slabs together. I really don't think you just need to have that much of very complex analysis to do that one. Use what is written in the code. If it is not given in the code, if you has to calculate, use this approach to calculate that one. Any questions up to now? No. So now I spend over 3 hours. Shall I talk about the thermal effect? It will take about another 15-20 minutes. Can someone, yes or no? Continue?
Yes.
Okay, thank you. Yeah. So the thermal effect on the bridge. Yeah. Day and night all the time. In Sri Lanka, so we don't get that much of seasonal changes, but if you go to up country area, you will feel that one. Cold weather, hot weather, but these standard, especially the Euro standard, and in Australia we have a seasonal changes. So because of that, all these standard develop in our in these countries. We have a seasonal changes. Because of that, the thermal effect, the way they consider to capture these countries, like for example, the Australia also got a very cold and very hot climate areas. They develop to cater all those things. Before we get into that one, thermal effect. Okay, we know thermal effect, temperature goes up and down, expansion, contraction, two in the bridge. And that's developed complex stress system. Makes sense. Thermal contraction, expansion, same exactly like braking and traction, right? Do the same thing. If you get this bridge, thermal contraction, contraction and expansion, what is going to do to this bridge? Because this bridge got an expansion joint at the two end, right? Complex geometry is produced very complex kind of a stress and load system. When we say complex, when we apply the load, because it will produce like every location in this bridge. When we say complex, I think we don't want to use that word because we are good structural engineers. I say, no, I don't like that word. But every time I go in here, I can resolve that one to 2 or 3 direction maximum. So I represent that load in terms of 3 components in every point, and I analyze my bridge. Yeah. So I say complex because you need to do the modeling and analysis to understand them better, get the right outcome. Of course, the thermal effect, the bridge contract, expand and contract, it will affect it's affect the bridge articulation, fixity, calculation of the expansion joint. Yeah, all those things we need to know. And it's affect the bridge geometry. I'm not going to jump into this one now. You will see this one very clearly in the next slide. It generates residual stress. That's what I put this box girder cross section in here. This affect the residual stress. When I say the complex stretch, this industrial ring road picture on the top will produce the complex stretch system. But one in the bottom, this is the infra 2 in this Super T girder bridge, 304 meters inland. But this produces stresses, but not as complex as one on the top. We have a residual stresses. We will discuss about that. Why do we have a residual stresses in a bridge? Okay, you know we talk about residual stresses in the steel, right? Especially the cold work like welding and things, right? And we got a residual stress when we bend it, right? Similar to that one in the bridge also, because of the thermal effect, we get a residual stresses. The temperature effects significantly affect our serviceability limit state design or SLS design. It's quite critical. That's why in my first slide, with the permanent effect, with the live load effect, I combine a thermal effect. Give me a one.
Sir, we can hear you.
Sorry. We combine permanent effect, traffic load effect with the thermal effect. The reason is because same as the traffic, thermal effect we get every day in a different way. In the next slide, you're going to understand it. Is it clear, this one? Expansion, contraction is quite obvious one. Articulation, okay. Bridge, expand, contract is effect. The complex stress, okay, with that one makes sense. And then the residual stresses, yeah, I will explain it to you why. In these different cross sections, for example, this is a really wide closed box section, right? And sometimes you have high girder bridges, steel bridges, right? With the deck, we'll see why we have a residual stresses. The reason, if you need to have a residual stresses in a bridge, right? You need to have a complex temperature distribution in the bridge, cross section, longitudinal or through the cross section. Let's see how it's going to happen. Okay, this is the typical bridge cross section. We got a sun, we got a radiation. In the bridge deck, I didn't show the barrier. We have a barrier, it's reflected. We got a wind all the time, right? Because when there's reflected radiation, re-radiation, because sometimes really heat, I think, because especially, you know, the hot days when if you are driving, you can't walk on a bridge, it's really hot, right? And you can see on the bottom, it's like we are staying in the house. The people have a problem driving on the top, but you can easily live underneath the bridge. It's shaded, right? So on the top of the bridge in that area, you got a ambient temperature, air temperature. On the bottom, you got air temperature, but these are different. In this, on the area close to this bridge surface, it's not the same. So then, because of the solar radiation, it's changed with the time. It may be really hot in the afternoon, but cold in the morning, hot in the afternoon, again cool down in the evening. But if it is a day with the moon is more cold on the surface in the night, right? This surface will behave differently. And the air temperature also fluctuate because of the movement of the sun and the wind. It's not a constant speed. You got a heavy wind, you got a slow wind. Sometimes you feel like there is no wind at all. And this material property, it could be steel, it could be concrete, but sometimes bridge deck is concrete, but we got a wearing course, the asphalt we put on the top, right? And then we got a surface characteristic of the bridge deck. They are very different because the deck you made from some deck you straight away made from concrete, another one you put the asphalt. And the bridge cross section and the bridge span, they are different. You can have a high girder bridge, you got a box girder bridge, you got a closed cell bridge, you got a twin cell bridge, you got so many different bridge cross section. All sort of thing will happen in the bridge. The section in the top, because of this temperature really high on the top, temperature is really low on the bottom, that contribute to a variation of temperature across the bridge cross section. This temperature, what we call the differential temperature variation across the bridge cross section, relative variation from top to the mid. Because this you can, if you do a transient heat analysis using strand 7, you can get a better understanding about this one. You can do if you want to, yeah. But codes gives you this value. I just want you to understand why we are getting that one, because this complex changes happening in the bridge, we get this residual differential stress distribution across the bridge. And in the bottom also we got, but it's a very different one to the top. Because of this differential temperature variation in the top and bottom, in your bridge, you're going to get complex residual stresses. I don't have example in here. I will work out a one, and I will put in the resource folder. You can see that example. Is it clear why we get the now you can understand why we are going to get the complex residual stress within the bridge cross section. When you are designing continuous span bridge like that, that residual stress distribution have a significant impact when you design for the serviceability limit state. That is very different when you design a bridge the straight line, kind of a straight bridge sitting on the elastomeric bearing. Yeah, it's very different. If you design a continuous span bridge, this affect significantly affect, because you see there is no uniformly distribution temperature in here. If you know temperature is proportionate to strain, this temperature distribution is like that, then your strain distribution within that cross section represent exactly the same. If you know the strain, you can easily calculate equivalent bending, axial, and the residual forces in the structure. I will do an example. I will show it to you. Then you will see, because of this differential stress distribution, there is always residual stress within the bridge. So we need to be really careful when we were designing this one. So when we were designing the bridge, to calculate the thermal expansion contraction, you should be able to decide what is the bridge temperature. Because you know, when you build bridges in different locations, it's a very complex thing, similar to what we talk about in the like traffic. So the different design codes have a different approach, but this one you need to use the local the annexes, the recommendation given to you. I think in Sri Lanka, for example, should say the SLS, Sri Lanka Standard Institute, right? I think you have to use. If not, I just look at in terms of the Australian perspective, the continent, like in the tropical area, like in the Darwin, in that area, they see the bridge. When we are designing, you calculate your average shaded air temperature in the bridge. You can assume maximum go up to 44, minimum go up to 4 degrees, and corresponding to that, there is a correlation. They develop this relationship. If you know these numbers, using the average bridge temperature, you can interpolate and you can estimate what is the average bridge temperature. So depending on the location, depending on the region, or depending on the value given to you, you can either calculate the maximum and minimum bridge temperatures, or else you can use the numbers specified in the contract or in the annexures. So in this calculation for the Sri Lankan scenarios, I just say if you don't have numbers, it's better to use the region one is on the area in here on the top, like a Darwin, and the tropical area, the coastal environment 44 and 4 degrees, because we talk about the elevation higher, less than 1,000 meters. That's shaded air temperature is 44 and 4. If we work out the corresponding temperature, bridge temperatures, if you go to the on the bottom area of the column, the 42 shade air temperature, shade air temperature 42 corresponding to average bridge temperature 46, and the shade air temperature 46 corresponding to 40, then the 44 is the average of these two. If you 50 plus 46 divided by 2, 48, and your minimum corresponding to 4 degree is straight away you can read. For shade air temperature is 4, then the corresponding average bridge temperature is 8. So the variation is 40 degrees. If you assume your average bridge temperature in the Colombo or some other area, 15 degrees Celsius, you can see your temperature increase when you design the bridge, right? When you set your expansion joint, if your temperature is 25 degrees or 28 degrees, then the temperature increase is 20 degrees. If you set 28, your temperature decrease between 28 and 8, again 20 degrees. If you set your bridge expansion joint and you assume in your design is a 30 degrees, in the variation, temperature higher, go up is 18, go down is 22. You can decide that one. So because of this, the radiation on the bridge deck, because of the different bridge configuration, bridge superstructure, the distribution of the temperature given in these tables. This is, for example, concrete eye girder bridges, or as closed form or box girder bridges. This temperature distribution, you can see, is the parabolic variation. The variation is within the top 300 millimeter or thickness of your deck, because 300, you don't have this temperature distribution in here, thickness of your deck. And then similar to steel structures, we have a different temperature distribution. You can use it. Again, this distribution, the values T, it need to be specified. It need to be specified in the design annexures. If not, as corresponding to like Australian context, like a Brisbane, Darwin, the 14-degree differential temperature. If you use on a concrete box girder kind of a bridge, the 14 is on the top, and within 200, you will get that one to, it will reduce down to 0. For this, I will do a simple example for you to understand this one. Why we are this temperature distribution, what is this looks like, and we convert this same diagram into a strain diagram. From that one, we convert that one to a stress diagram. Then we get the axial and bending and the residual stresses within the cross section. Then I will show you to. I will give you one simple example, because the when you calculate this one, depend on your bridge cross section, this thing will be changed significantly. Yeah, I will just give you one example. When you change the bridge cross section, you change your I values actually and A values, then you can change your stress diagram accordingly. Yeah, this is the one example I just do for thermal effect. The maximum bridge the length of the bridge is 304 meters to 14 meters. The expansion thermal coefficient of thermal expansion is 1 into 10 to the power minus 5. Normally it got a 20% variation. That's of course say plus or minus. And then we got a average bridge temperature 20 degrees. The maximum bridge temperature from that calculation, we can calculate that one, depend on the location of the bridge, 48 degree, minimum is 5 degree. When we were average bridge temperature in that area, we considered as a 20. So then we can calculate what is the bridge expansion. It's very easy to calculate because the length of the bridge is L is 314 meters and alpha is 10 to the power minus 5. And the temperature increase is 28 degrees. You can easily calculate L delta T time L, alpha time delta T time L. So alpha is 10 to the power minus 5, delta T is 28, L is 314 meters or time 10 to the power 3 millimeters. Your expansion is 88 millimeters. It's quite large. I put this value within the bracket. Your coefficient can increase 20% or reduce 20%. That number will vary from 106 to 70. So your expansion can vary between 106 to 70, similar to the contraction, because your temperature, lowest temperature in the bridge could be average with temperature from 15 degree contraction. Then if you do the calcs, it will be 47, or else if you get the fluctuation, it varies between 56 to 38. And if you multiply this one, because this is quite a lot of unknown, if you multiply this one using a load factor 1.25, that's what we use in the Australian standard, your expansion becoming 110, your contraction becoming 59, or else this variation, if you consider the variation in the thermal expansion coefficient is changed with 113 to 88. So you can see in this bridge, you got a contraction, an expansion in the ultimate case 110 and 60 millimeters. I should say when you calculate the thermal expansion and contraction, you should not use total L, it has to be L by 2. Yeah. And then the, oh no, sorry, is the L, sorry, L alpha T. Yeah, alpha delta T times L. So these numbers, any bridge you can calculate if you know the thermal expansion and contraction in the bridge. Because I want to say this bridge is sitting on elastomeric bearing. You can get this expansion and contraction in that way. If this bridge is a continuous span bridge, this thermal load need to be absorbed by the superstructure and substructure itself. Then the loads acting on the bridge will be significantly different. So you have a lot of significantly large stresses built up in the bridge in addition to the residual stresses. That is the end of my presentation. Do you have any questions? Please feel free to ask. The next presentation, I'm going to discuss about the application part 2. That's next Friday. So do you have any question for today's session?
Mr. Rohika, hello.
Yeah.
As Arthur, I have a question about what you spoke about earlier. It's not exactly about the loading condition, but about a point that you mentioned earlier, which is with regards to the cambering. You were saying in your experience that, no matter what calculation that you do, the cambering values are very different when it comes to practical situation. So I just want to know, how do you practically, how do you tackle that situation?
Yeah, that's a good question. Yeah, this is, I'm going to actually explain in detail when we were designing the bridge drawing. We tabulate that one. For example, the when we were constructing bridge in the design stage, we assume the bridge is going to cast within a day or two. They bring it to the site after 28 days. They're going to erect after 40 days later. We're going to cast the deck 60 days later because we need to fix the reinforcement and thing. And like that, we can make those assumptions, right? So we can do our camber calculation. But what we do normally when we designing the pre-stressed concrete member, we assume we're going to erect the girder onto the bridge, onto the bearing, the 28 day. So we calculate the camber. Because in the bridge articulation tomorrow, the next session, I'm going to explain the bit camber have a significant effect the way we're going to sit the bearing seating arrangement we are designing on the bridge, right? We call epoxy block. That's a technical term we used in here when we are designing that. To tackle that one, what we do, we give the contractors many different camber values. We give 28 day, what is 60 day, what is 90 day, those values we give. And when they were constructing the bridge, they need to measure, they need to estimate exactly when they're going to place this bridge onto the bridge, place the bridge on the bearing. They need to estimate exact date, and they need to calculate actual camber in the girder. And using those data, because our predicted values, the predicted value in the sense we gave them numbers to develop their what I call the epoxy mortar block, that the element or concrete unit between the girder and the bearing. That unit we pre-molded that one, and that one we give different values, like a 28 day camber, like a different cambers. We gave many solutions. Then what the contractors will do, they will calculate the actual one, then they will interpolate between the other values. They were quite accurate because if we give the numbers very close, it's all worked in the site. Yeah. Did I answer? Did I explain it to you correctly, Arthur?
Yeah, yeah. Thank
Yeah.
you.
Yeah, because the I will show that numbers in the bridge articulation. The one I will show you one example. Yeah, because because this camber value they need to measure. Yeah, so it's a quite a difficult thing to do, but has to do. Yeah, but now with the technologies, it's not that difficult. You place it and you put a laser, you can easily measure that one. Yeah, but in the olden day, it's quite difficult one. Any more questions?
Hello, Mr. Rohita.
Yeah.
Yeah, I'm Malit here. That I have one question regarding that 80 kilonewton single wheel load. So it's about the application of the single wheel load because in BSc standard we have 100 kilonewton single wheel load. So I am quite doubt where to apply that load. I mean, if we check design the deck slab, do we have to check the punching shear or any other criteria do we need to check with that single wheel load or something? I want to know about that thing.
Yeah, okay. I think the single wheel load, I think because the go to, yeah, if I explain it to you, that one, I think there is a general design philosophy in the bridge design. The punching shear is never going to get governed. The reason is if you design a bridge, your reinforcement is N16 or 16 millimeter diameter bars in 150 millimeter spacing. You got 4 layers of rios. Because of the tire pressure, it's not going to go through punching. Like if you go to like a standard like Astro, they said you don't want to check that one at all. But even if you design using the punching, because you can get your wheel load, the 80 kilonewton, or in the British standard 100 kilonewton load. So you can divide that one by your area load. You can calculate the punching shear like we just calculate the punching shear in the footing. But maybe in the design time, I will show you one example, because when we are designing in the concrete element, because we have the 4 layers of reinforcement, we call the reinforcement mesh on the top and bottom, that reinforcement will produce the tension in either side. Because of that, in the bridge deck design, the punching shear, I think we normally not check or not required, because the bridge deck are heavily reinforced for that. But you can put your 100 kilonewton wheel load to the extreme end, like in the LM2 load case in the Euro code. That's where the 400 kilonewton axle, we face against the tire is face against the barrier. So that will produce you the maximum sometime in the bending moment in the cantilever, the section of the slab. Like for example, if you design an I-girder bridge with the cantilever slab, you got your barrier at the edge. If you put your wheel load in there, it will give you the maximum bending. I just want to reiterate to this one. These two load case mainly we use when we were designing expansion joint, because if we use just the 80 kilonewton load or 100 kilonewton load close to the barrier face, or LM2 axle, A400 axle load on your bridge deck, please note that because the bridges are quite long, that load will distribute in the longitudinal direction. Because the I don't think you can see me, but I will draw sketches and I will put this one graphically for you to understand. Because the load will distribute, let's say the 45-degree angle, for example. If your cantilever length is 1.1 meter, 1 meter, let's say, from the center of the load to the face of the center of the cantilever 1 meter, if you assume 45-degree, your distribution length is 2 meter. So that bending will resist by the 2 meter long section in your face of the the cantilever. Because of that, this application is this load sometimes is not directly governed. But if you design expansion joint, because they are in the width of the expansion joint is not like long as the bridge. It's a very small section. Sometimes those design is covered. In addition to that, because we amplify that one using a larger dynamic magnification factor. If I answer to your question directly, these two load we mainly design for checking the expansion joint design, but it's better to use this one in your grillage model, or else the distribution I mentioned, just do a hand calculation to see. For example, if you're 1000, if I just give you numbers, if you use if you write it down, your point load is 100 kilonewton, your distance to your cantilever section is 1 meter. So then your bending moment, if you calculate 100 times 1 is 100 kilonewton meter. So if you assume 45-degree angle distribution, forget about the width of the wheel, then 45-degree mean is go 2 meter width. So then if you are 100 kilometer distribute over the length of 2 meter. So if you convert into normalize that one, if you divide it by 2, you get a 50 kilonewton meter load within your in your cantilever section because of your 100 kilonewton meter load. That is how very simple analogy, the way that load is translate into your calculation. But if you run, of course, with the grillage model, you may get a little bit different answer. Did I answer?
Yeah, yes, Mr. Rohit, thank you very much. So I have used this 100 kilonewton and the HB vehicle load in the grillage analysis, and then I got the HB vehicle load was the most critical one for the deck analysis and the overhand design. So I had some doubt about this 100 kilonewton. So that's why I asked from that question. Then I have another simple question to clarify something, get some clarification. So we have in BS code we have load called knife edge load, knife edge load along with the HAUDL. So
it's the
I
same
didn't
thing.
see
The
yeah, I
knife
didn't.
edge load is, I think it's the same one in the Euro code. You got a this tandem load got a 4 axle. That's got a 600 kilonewton. It's simply replaced with the one point load. The knife edge load mean the 1 point load, because I think the code simplified back then. You can, it's most of the time the designers they did the calculation, the hand calculation. So you have a UDL and a single point load along the your bridge. Is very easy to calculate, because you can use the influence line diagram. From that one you can generate your bending moment and shear force diagram very easily. That's the reason I think the code had that simplification. But I think now the BS code also, I think they changed back to Euro code. But now I think in the current standard practice is the LM one. Yeah.
Yeah, thank you very much, Mr. Rohit. So I have designed only for VS codes in here, Sri Lanka. I have no experience about the that Euro code and other codes. So that's why I asked that question.
Yeah, of course, yeah. But both the approach in all the codes are the same. Yeah.
Yeah. Okay. Thank you.
Any more questions, please?
Hi, Rohit. It's Sean here. Can you hear me?
Yeah, Sean.
Yeah, thank you very much, firstly, for conducting this session and all your efforts to prepare this informative presentation. I know especially how much you are busy with your work schedules, and I feel it's really useful and for anyone who is interested to design bridges. And regarding loading, I would like to ask a small question that might be helpful for everyone. Then we have discussed about vertical load distribution across transverse direction according to lane factors. In longitudinal direction, most of the time we only run one truck along the bridge, and why we are not running multiple trucks one after one for designing bridges? Is there any reason for that? For in the practical situation, there might be another truck behind the given truck.
I think because Shanti, like if I go back to the first slide, when we were talk about you can see this situation. The weight of this truck is 62.5. That's the standard B double truck. So we can have this truck 30 meter, if average 35 meter spacing. If 100 meter long bridge, we can have 3 trucks, one after another. Light, if you see the total weight we are putting on that lane is equal to about 200 ton or 2000 kilonewton. But when we look at the M1600, the load effect, we get for that single truck within in terms of the weight, I said it's much higher. And the other thing I have experience because I tested more than 10 bridges when I was in Bangkok. I wrote a paper about that one. I will share about with you. I wrote a paper in the sense we group, and we designed those bridges using the ASHTO code. We use the lane load and a single small truck. But we tested those bridges for the truck train, like a 10-wheeler trucks. We call truck train. They're placing each other next to each other, close to each other. We tested those bridges. Yeah, we don't have a problem because like I mentioned in here, this box, because of this so many variabilities, so many analysis, the one way the structural modeling, but not much maybe, but a lot they analyze this one. And the variation with the load factors and other thing, what is the probability that this particular environment, if you run a heavy truck train along that one, what is the stress or bending stress or the shear stress, the peak values on those bridges in the locations. Yeah, they got understanding. That's how they develop that one. But they still allow like a 5% of the if you send, like for example, you haven't seen this one even in here or even in Sri Lanka, like in Bangkok when you were building all these elevated 20-30 kilometer long the bridges, especially segmental box girder bridges, they got about 30-40 trucks is come one after another. 30-40 trucks come one after another is pass all the bridges. Yeah, that sort of situation is there. But I think as the still this design codes, I think cover that one. But some road agencies, they ask designers to do the test. I think there are, if you go to Google and if you looked at, there are some bridges. I think they build long span bridges in the valley. They loaded that bridge with few hundred trucks and they tested. Yeah, they all tested. Yeah, but in general, this is need to come from the road agencies because as you know, they know that this is working, but there's an extra cost for them because of that. They don't ask, but it's working because my experience in the Bangkok is a part of the contract. We have to test the bridge for that particular truck train because we are designing bridges to ASHTO standard, very different, but we tested them. It's all work. Maybe I will share with you all some of this information. I just need to find. Is that did I answer?
Yeah. Yes, thank you very much. And I just thought because if it is a continuous bridge, then because of the alternative arrangement of bending, then there might be some cases, worst cases with the given span that might be 2 vehicles, and then one span could be higher bending than normal single truck.
This is what if I further add to this one. I think we call the Caltran trucks. I think in the state of California and the USA, they use the series of trucks in their designs. Yeah, but for example, this is something we that we can do normally. If you are testing an existing bridge, for example, this B-double truck, we know this axle load exactly. They have a load limits, and these are quite accurate. We can put this one in our grillage model, and we can run these in a close spacing in a legal limits, like even as close as possible, and we can run along that one, and then we can see the impact on the bridge, and we can compare the same thing again, M1600 or LM1 load in it to the Euro code. Yeah, we can verify the bridges like that. But
yeah, because
yeah, we can do. But I think in the Caltran, yeah, I think the Caltran, they got a truck loading. So yeah, even I'm not, I think this is, I'm not, in my memory, maybe I'm not right, but I think the Japanese standard also, I think they use a truck train in their bridge modeling. Yeah.
Thank you very much.
Any more questions?
Yeah,
just thanks Rohita for the marvelous presentations always. I enjoy very much. And just one comment on from Transport News out there. We are the clients.
Yeah.
Trucks, some of the trucks we are running on certain roads are way heavier than these normal B-doubles.
Yeah.
And we test them before we allow them on the road, and that particular route is load tested. That's how we introduce to the network. It takes some time, boil them down to the design standards. Yeah, Botany Port, there are trucks running at 78 tons at the moment, and also Botany Port, they have asked to increase it to 100, like super B doubles. Okay, so that's how it is. It takes time them to come down to the design section, and up until then we will test, as you said, we are testing load testing all the bridges.
Yeah, I think that's really right, because they, especially I think this is the bridge in my background, that is the bill purposely to transport the cargo from the port in here. In the port area, sometime I think they like in the Eurocode in here, they design for a special loads. I think the special loads and the combination to match with the requirement. Only this particular bridges, especially this one, for example, design and yeah, because it's need to have some certain understanding between the port operators and the client, because they need to tell we want to operate this one, then the client actually can talk to the designers, and then their own design teams, and then can design those to cater them. Because the only thing like the bridges, if we send with the overload truck, it's quite common around the world. I think if you design with the overload truck, the design life of the bearing and the expansion joint, yeah, sometimes you can say it's exponentially reduced. Yeah, that is the main problem. And even sometimes the bridge vibration, the fatigue effect and thing. If I just give the example, these are not the numbers, just my reading and understanding. If a fatigue effect of the car versus the truck is more than 1,000 times, yeah. So if you just put the more trucks, heavier trucks in there, that will amplify more. Then that reduce especially if it is a steel bridges, the design life of the bridge will reduce significantly. Thank you very much. This the comment and suggestions, Ravi.
Okay.
Thanks.
Okay,
Thank
thanks.
you. Any more questions?
Mr. Rohita, I have one and the single question. So I want to get to know about the effect of the settlement on the superstructure. So are there any relations for the span and the allowable settlement in the bridge designs? So can you give me a small idea about that one also?
Yeah, I think there are two ways to look at that one. You can do a 3D model with the soil structure interaction. For example, you you can model the end bearing if it is on the sand or if it is on the rock. If it's on the rock, you don't have a differential settlement issues. If it is in the sand, you can use the dose of spring constant. You can vary that one. You can get that. I think if I give you, I can send you some need to find, but in memory, I think L over 360 is the number. If it is go beyond that one, I think it will crack the concrete. Did I answer your question?
Yeah, okay. Thank you, Mr. Rohit.
You will spend the L over 360 because normally we design bridge for close to, like in the ASHTO is close to L over 800. In Australian standard is L over 600, but when we design is close to more than L over 800, the lie load deflection, but the differential settlement of the settlement, if you get your sag on the bridge, it's more than L over 360. I think there's a relationship. Yeah, you can easily calculate what is the tensile stress in your bottom of your cross section, and then yeah, people do this stress analysis using the deflection. They got this correlation and then work out to be roughly L over 360. But when we were designing a bridge, we can't design it to crack. So you need to make sure that you looked after you articulate the bridge to absorb that differential settlement. Any more questions? Did I answer? Did I give you enough explanation to your question?
Yes, of course, Mr. Rohit. Thank you very much.
Thank you. So if not any more questions, so then we'll see you next Friday evening. Then I will put whatever the resources related to this thing I have in the resource folder. I think you can access to that one, that Google Drive. I think the presentation slides also there. So thank you very much. It's almost 4 hours for you all also. Now I think it's 4 o'clock in Colombo, right? So thank you so much. And then please feel free to share this presentation with your friends. Yeah. And thank you very much, Chatumi and Dilina, and then Shiromal and CSEC for yeah, organizing this one. Thank you very much, everyone. So have a good evening and good weekend. Stay safe. Good night.
Okay, thank you.